4 dimensions. So the first two equations you get are nothing but the Bianchi identity for the vector fields. The second equations you get here are nothing but the equations of motion for the vector fields, where again F1 tilde and F2 tilde are nothing but, this is like a shorthand notation for this. This is what is called, so essentially this is the usual electromagnetic duality in 4 dimensions, in which the Bianchi identities and the equations of motion can be treated democratically. And essentially these are the magnetic field strengths, which are not independent from the electric ones. In particular, you have these self-duality relations. And then you also get the equations of motion for the complex scalar tau, the one that follow from this action, and also the Einstein equation that follow from this action. So in the end of the day, you start from the 11D equations, you plug an ansatz, and then these equations really reduce to the equations of motion of the 4-dimensional theory, precisely the equations that follow from this action. Okay, this is what people mean by having a consistent truncation. So let me go back to the action. So this is the 4-dimensional action, and what kind of solutions people have explored here. So people, first of all, study solutions in which only the rich scalar and the scalar potential are there. So essentially, configurations where the scalars are constant, in particular the complex scalar tau is 0. And in this solution, so it's I in this parameterization, sorry. And this is an ADS4 solution that when you place it in 11 dimensions, what you get is the famous ADS4 cross S7 Freund-Rubin solution. Okay? And then we know now, after many years, that this ADS4 vacuum that uplifts in 11 dimensions to ADS4 cross S7 is precisely dual to the 3-dimensional conformal field theory of ABJM. Okay? So ABJM is the field theory dual of this specific ADS4 solution. But then you can search for more complicated solutions. For example, solutions in which the scalar fields develop a profile along certain direction, certain radial direction, let's call it. In this case, you can construct some type of solution that is called a Janus. So a Janus is a 4-dimensional solution, which is not ADS4, it's ADS3 times some radial direction. And the ADS3 is a proper ADS3. It's not a warp ADS3 in the sense of the type we heard about this morning. I will come back to this at the end. So this is just an ADS3 solution in 4 dimensions that once you place it in 11D, it goes to an ADS3 cross some radial direction, cross S7. And then these solutions are dual to what is called interfaces in ABJM. So essentially configurations in the field theory in which you have the field theory living in two half spaces and there are certain properties changing from one side to the other. And the change of the properties in the field theory from one half to the other half of the space is related to the running of the scalar fields. And of course, there have been a lot of works on ABJM interfaces or equivalently Janus solutions in the gravity side. And then maybe the most studied type of solutions are solutions of the form ADS2 cross sigma 2, which are examples of black holes which are asymptotically ADS. Okay? So in this case, what you have is a solution in which everybody is activated, vectors, scalars, everyone runs. So they are like complicated solutions, let's say. And essentially what you get is that they are in ADS because there is a cosmological constant. So in the end of the day, you have solutions that interpolate between an ADS4 in the UV and the horizon configuration, which is the ADS2 cross sigma 2. And this holographically describes, in field theory, the ABJM theory. When you place it on a Riemann surface, then you have to add a topological twist and certain things, and you describe essentially like flows across dimensions in the field theory. And there is a really long, vast literature on this kind of configurations. Okay? So all these things have been done in this 4-dimensional supergravity for which an embedding in 11D is known. Okay? So what I will tell you today is that all these solutions, absolutely all these solutions that have been embedded in 11 dimensions can alternatively, and this is the really important message, I will pass it today, can be uplifted to type 2B as well. And the whole meaning of the story is not known in type 2B. So there are 25 years of research on ABJM and all these solutions, and I will show today that this exact same theory can be embedded in type 2B supergravity. And the configurations in 10 dimensions will be of the form what is called as an S-fold, okay? So this is the main message. Any solution of n equals 4, d equals 4 supergravity, and also n equals 3 and n equals 2, because they are subcases, can be oxidized to a configuration, which is a non-geometric configuration. I will explain this. That is called an S-fold of type 2B string theory. So everything that has been done in the context of 11-dimensional supergravity and AVGM can be repeated or reinterpreted in this context of type 2B S-folds. So the holography has not been explored. So the outlook of the talk is the following. First of all is what is an S-fold, because most of you maybe never heard about an S-fold. So what is an S-fold configuration of type 2B? And the second is just how to place n equals 4, d equals 4 supergravity in type 2B. Actually, this was our paper. Our paper was to take this theory, place it in type 2B, compute the equations of motion of type 2B, and finding precisely the equations of motion that are in this box. Okay? It's like an alternative path to uplift n equals 4, d equals 4 supergravity, which has not been explored. Okay? Yeah, the uplift to 11D, so it goes through the 7 sphere, and then depending on the solution that you have, if you have a black hole, if you have a Janus, if you have whatever solution you have, then the 7 sphere will be distorted in one way or another, depending on what the scalars do, what the vectors do, but the topology is always the 7 sphere with different deformations. In type 2 is going to be something else, I will show you. So, good. So what is an S-fold? Let me start from a solution you all know. Take type 2B supergravity and place it on ADS5 cross S5. This is not an S-fold. This is ADS5 cross S5 solution of type 2B supergravity. So the geometry is like this. The ADS5 part, the 5-sphere part is a round 5-sphere. That's why there is an S6 symmetry, which is the asymmetry of superjump mills and so on. Then the radius of the ADS5, I call it G minus 1. So the radius of the ADS5 and the radius of the S5, they are related. They are the same. Then there is a 5-form flux, as you know. And then there is the B2 and the C2 that I put together in this SL2 vector, which are 0 in the ADS5 cross S5 solution. And then there is the action and the dilaton, the Ramon-Ramon 0 form and the dilaton phi, that I will describe them by placing them into this 2x2 matrix that I call M. And then you know that for the ADS5 cross S5 solution, the action is 0, so this matrix is diagonal, and the value of the dilaton is a free parameter in the ADS5 cross S5 solution. So in the end, there are two free parameters, G and the value of the dilaton. And for the rest of the talk, I will fix them like this, just to remove them. But you can always reinsert different values if you want, okay? So I will fix, just for simplicity of notation, G equals 1 and phi 0 equals 0, okay? So this is ADS5 cross S5. But then this workshop is called, it has to do with low-dimensional holography. So you can ask yourself the question, can I replace for free ADS5, which is for dimensional field theory, can I replace it by ADS4, so I have low-dimensional holography? And then I will try to replace ADS5 by ADS4 cross a circle. So what happens if you do that? Does it work? And the answer is no, it does not work. What else you have to do? And then you have to do the following thing. So you replace ADS5, as I said, by ADS4 cross S1. This is good. You don't touch the F5. This is okay. Then this is again the B field. They are 0, as they were in the ADS5 cross S5. This is good. And the only thing you need to do is sort of like a minimal modification. You just have to take the action dilaton matrix. The action is 0, and the dilaton is just linear on eta. And if you evaluate the supersymmetry of the solution is non-supersymmetric, that's life. And the dilaton develops a linear profile. Then, Monica said this morning, who cares about solutions with a linear profile for the dilaton? I will care about solutions with a linear profile of the dilaton. Okay, so essentially, this talk is all about considering the linear dilaton profile seriously. Okay? So what happens? So I have this solution. Then, as Monica pointed out, how do you make sense of a linear dilaton profile, right? Because it sounds pathological, no? If it is linear and you make a circle, what is that? I mean, it's not single valued. Shall I throw away the solution? Let's keep the solution for the moment. So, yeah?
It's kind of similar, like, I mean, to big brains, like, I mean, with E not equal to 3, right? I mean, like, there you also have this kind of...
So I'm thinking of the D2 brane. Yeah, the D2 brane is non-conformal. So this case is, in that sense, yes. I mean, it's like In the deep brains, there is a moment in which the dilaton blows up really as a singularity, and this is more like a linear thing. I mean, it goes to infinity in one side, and yeah. So the thing is that, yeah, so we have a dilaton with a linear profile. And the next question is, can we make sense of this? Can we make sense of a dilaton with a linear profile? And then, in order to make sense of the solution, the only thing I will do is to rewrite this exact same solution in a more fancy way. What is the more fancy way? So what I'm going to show now is exactly the same slide as this, but just rewritten in a funky manner. So this same solution can be written like this. Okay? So what is this? So this is the following. So the entire dependence on the eta coordinate, which is the coordinate along the S1, if you look at this, for example, you get e to the minus 2 eta for the dilaton. This is precisely what you get in here if this math frac M is just the identity matrix, and this A matrix here is this twist matrix over here. So what I observed by rewriting the solution like this is the following. The B fields, which were 0, they can be seen as the A twist acting on a vector of zeros. So this is sort of trivial, right? But then the axion dilaton matrix can be seen as the identity matrix being twisted by this A matrix. The geometry is the same, and F5 is the same. So what you learn from this is that a linear dilaton profile can be seen as a configuration in which all the dependence on the eta coordinate, which is the coordinate on the circle, is codified into this A matrix that is called a twist. Okay? It's just a way of really rewriting the same solution. But this is more illustrative. Why? Because what we learn from this is that what is happening is the following. Oh, there is something that is not displayed, eh? Ah, what a pity. So it's not, it's a pity, it's not, shit, it's not. Yeah, so I call this A because I decided that the way of twisting the B field is A, and the B field was defined with an index up, and therefore the M alpha beta matrix has the index down, and it must be twisted by the inverse of the matrix. It's just conventions. It's a pity because the next slide was really, it was a cool one. No, the other ones are fine, but the thing is that there was an equation here which was very important. Okay, well, let me try to explain the equation that is not there. So it's not my eye, no? It's not there. No one can see it, right? Okay, so let me explain with words what was in the equation. The whole point about this solution is that the entire dependence on the coordinate along the circle is codified in this A matrix, which is, by the way, an element of SL2, because you can see that the determinant is 1. So let's see how this matrix is appearing. And this matrix is precisely appearing in all the type 2B fields which are transforming under the SL2 symmetry of type 2B, which is called S-duality, right? So you see that the B field is twisted by the A matrix. In this case, it's trivial, but it's twisted by the A matrix. The axion dilaton, which is encoded in this M alpha beta, is twisted accordingly because these two fields transform under SL2. And then the geometry and the Ramon-Ramon form potential, which are SL2 singlets, they are not affected by the SL2 twist. So it's a way of knowing or somehow like clarifying the role of this SL2 matrix A and how this linear dilaton solution can be encoded as an A-twisted solution. So imagine I take this matrix A. I'm going to say that there is a circle spanned by this coordinate eta and of period t. So how do you evaluate whether a solution has a monodromy or not? You take this matrix A at eta equals 0, and then you evaluate the inverse of this matrix at eta equals t after going around, and then you multiply the two. So you multiply A of t times A inverse A of 0 times A inverse at t. And if there is no monodromy, then that thing is essentially is the identity, because you get A minus 1, you get the identity. It's a pity that this is the equation that is missing here, right? So if you compute A of 0 times A inverse at t, you get something different from 0. You get e to the minus t, e to the plus t, which is essentially telling you that the solution has a non-trivial SL2 monodromy. And this is why these solutions are called S-folds. And essentially what is going on is that in order to interpret the solution, you have one patch which is going once around the circle, but then once you go around the circle, you have to glue the solution with an SL2 transformation that induces an SL2 monodromy. And this is why it's called an S-fold. And this is allowed in string theory, because in string theory, you can glue different patches by using not only diffeomorphisms, but also using duality transformations. And this is an S-fold because of that, because once you go around the circle, you have to glue the solution in one patch to the solution in another patch by an SL2 transformation. That's why it's called an S-fold. There must be something localized there, but this is an interpretation of objects and so on, which goes beyond the supergravity approach I'm doing. Okay. Yeah, there must be some kind of object triggering the S-folding somehow. So, yeah, so then, as I said, the monodromy is e to the minus t, e to the plus t. And that is an element of SL2R. So you can tell me, no, but the string theory is nothing to do with SL2R. It has to do with SL2 set, because it's a discrete SL2. And then there is a way of making the SL2R monodromy, make it SL2 set. And the only thing you have to do is to go for a different solution that is created from the original one just by acting with this constant SL2. So the original monodromy, which was SL2R, now becomes precisely this monodromy here. So the monodromy now is SL2 set, and this is a proper background of type 2B string theory. Okay. So after people discovered these S-folds, in particular the S-fold that I just described, which is non-supersymmetric, then people were asking themselves, like, okay, is there a way of making a supersymmetric S-fold? And the answer was yes. And then people came out with this S-fold, which this time is n equals to 4. So it really preserves 16 supercharges out of the 32 supercharges of type 2B supergravity. So if you look at the solution, now the solution is a little bit more complicated because the geometry is more complicated. So the 5-sphere is spanned by these 3 terms here. So you have one coordinate, which is alpha, and then a 2-sphere here, a 2-sphere there. So the geometry breaks the isometries of the original S5, but that's life. It's not a problem. Then F5 is like this. And then, as I said, it is an S-fold because the B field is, again, the A twist of this B1 and B2, which are eta independent. And in the same manner, the action dilaton matrix is the A twist of this matrix, which is, again, eta independent. So it's just a more complicated solution, but the structure is the one of an S-fold. It's really all the dependence on the eta coordinate goes through the twist matrix. And this S-fold, this solution preserves, as I said, n equals 4 supersymmetry. So 16 supercharges. So then we just ended asking ourselves whether the conjecture by Gauntlet and Varela was correct or not, because some years ago, actually quite some years ago, they made the following conjecture. So any supergravity, in this case type 2B, any supergravity solution with a d-dimensional ADS factor, in this case the S-fold, which has an ADS4 factor, preserving n supersymmetries, in this case n equals 4, defines a consistent truncation of the corresponding supergravity, in this case type 2B, down to pure n equals 4, d equals 4 supergravity. So if this conjecture was correct, and indeed it is correct because it was proven by David and collaborators in this paper, a consistent truncation of type 2B supergravity on the S1 cross S5 must exist down to pure n equals 4, d equals 4 supergravity. So in the same way as there was a consistent truncation to 11D by Sveti, Liu, and Pope, there must exist a consistent truncation of type 2B supergravity on S1 cross S5, this is the answer to your question, so it was on S1 cross S5, there must exist a type 2B consistent truncation down to pure n equals 4, d equals 4 supergravity. So equivalently, the field content of n equals 4, d equals 4 must be embedded in type 2B in such a way that any solution of the 4-dimensional supergravity will have an uplift not only to 11D, but an alternative uplift to type 2B. Okay? So then we try to work out this uplift. At the beginning, we were wondering whether there was some kind of group theoretic procedure to work out the type 2B embedding, but there was no standard group theoretic procedure to do it, as people have done in the past for other truncations. But then the good news is that now, these days, there is this framework of generalized geometry and exceptional field theory, and by exploring it, you can work out the consistent truncation. So this is a highly technical thing, but the nice thing, I mean, the only thing I want you to know is that in order to work the consistent truncation out, there is a recipe you can follow, which is, this is the recipe we figured out just by following or building upon previous results by Emmanuel and also by Davide and collaborators. And the point was the following. So if you don't understand this slide, it's fine. Like the point is the following. An n equals 4 solution of d equals 4 supergravity defines a generalized SU4 structure. Why? Because if the solution is n equals to 4, there will be an SU4 rotating the gravitini. So once you have a solution that preserves n equals to 4, that solution defines a very precise SU4, which is the SU4 preserved by supersymmetry. It's the SU4 of supersymmetry. Once you have this SU4, the next thing you have to do is to localize, to embed that SU4 in the exceptional E7 symmetry of 4-dimensional maximal supergravity. Once you have this, you fluctuate exceptional field theory about this solution. And finally, the dynamics of the fluctuations will happen to be described by the pure n equals 4, d equals 4 supergravity. This is a highly technical thing, but it's just to show you that there is a prescription to work it out. And the final outcome is the following. So this is the embedding of the 4-dimensional fields in the 10-dimensional metric. This is the embedding of the 4-dimensional fields on the axion dilaton. This is the embedding of the 4-dimensional fields on B2 and C2. And this is the embedding of the 4-dimensional fields in the 5 form of type 2B supergravity. So essentially, from the geometry, you see the following. The 10-dimensional geometry, it has the 4-dimensional piece and the internal part. The internal part is given by this expression here. So you see that the 5 sphere is distorted. So you have the alpha coordinate, a 2 sphere here, a 2 sphere there, and in front of these two spheres, you get two functions, f1 and f2, which are precisely functions of the complex scalar in the theory, the complex scalar tau that I said before, that there is in n equals 4, d equals 4 supergravity. The same for the dilaton and for the action. So this is the 10-dimensional dilaton, this is the 10-dimensional action, and then you can see your 4-dimensional fields, chi and psi, in the expressions, and also the function f0, which is given by this. So this is how to embed your 4-dimensional fields into the 10-dimensional scalars. Then the same for the B2. The whole thing is a bit more complicated. There is a component that is a scalar in 4 dimensions, and there are some components which are vector in 4 dimensions. And then you see that the scalar components depend on the scalars, and the vector components depend on the vectors of the 4-dimensional supergravity. So this is really like a plug-and-play thing. And then the F5 is a bit more complicated, so this is the 5-form field strength, and then you see that it depends on the field strength of the vector fields in 4 dimensions, F1, F2, and the self-dual F1 tilde and F2 tilde that I introduced at the very beginning of the talk. And then there are also these functions, B1 and B2, B tildes, which are written here. Okay? So the whole thing is that once you have a solution of pure n equals 4, d equals 4 supergravity, you can really plug it in here, and then you get a type 2B 10-dimensional solution. Okay? And nicely, the 10-dimensional self-duality of F5 boils down to the 4-dimensional self-duality between the vector fields. So it's something it's like a check that things are working properly. Okay? So how much time do I have? Because I'm essentially over. 20 minutes. Okay, this is going to be fun. This Docker et al. It is because in their case, they work out, if I remember properly, the most general solution, the local form of the most general solution preserving 16 supercharges. So locally, this will fit into their classification, and the whole thing here is about the global thing, the gluing of the global form of the solution, which is the gluing with the S-fold and so on. Okay? So essentially, now whenever you have a solution in the n equals 4, d equals 4 supergravity, you can decide whether to place it in 11D or to place it in type 2E. So then the outlook is the following. Take n equals 4, d equals 4, SO8 gauge supergravity with the field content I was saying before. So the first thing you can do is to place it in 11 dimensions through the ansatz by Svetich, Liu, and Pope. And the other thing you can do is to place it in type 2B on S5 cross S1 times the formula I showed you before. So now, what is going on now? If you just consider the ADS4 solution in this action, okay, in which the complex scalar is 0, and then you have an ADS4 solution, if you place it in 11 dimensions, you get an ADS4 which is dual to the 3-dimensional theory of AVJM. If you place it in type 2b, you get an ADS4 which is dual to the S-fold solution, which is called the S-fold CFT3 solution. If you compute now solutions which are ADS3, which are the Janus solution, if you place it in type 2 in 11 dimensions, you get what is called interfaces in AVJM. But then if you place it in type 2b, you would get what is called interfaces on these S-fold CFTs. And something I wanted to comment on this, because this is something we are working on at the moment. The Janus is precisely ADS3, and it only involves the scalars running. But something you can work out is what we will call the charge Janus, which is the Janus solution, but now you turn on charges for the vectors. This is a new type of solution you can construct, and what I can anticipate already is that once you turn on the charges, the effect is going to be the following. It's going to take the ADS3 of the Janus, and when you turn on the charges, the ADS3 is going to become a warp ADS3. So precisely when you write ADS3 as a Hopf vibration, ADS2 over a fiber, and you turn on the vector field along the fiber, precisely the effect of turning on this vector field is going to be deforming ADS3, keeping ADS2, and precisely ending up in the class of warp ADS3 solutions that we were hearing about this morning. So this might be a way of getting warp ADS3 in 11-dimensional supergravity or in type 2b supergravity, as you want. And it would be interesting to understand it in the context of either AVJM of the S-fold CFTs, and precisely to link to the talk by Monica this morning on this holography of the Kerr solution. So there is a way, it's just so there will be like this kind of warp ADS3 solutions we were listening about this morning. And then something else you can do is to compute black holes, asymptotically ADS black holes, in this supergravity here. Again, if you place it in 11D supergravity, then you will get the usual picture of AVGM placed on a Riemann surface. Then you turn on some topological twist, and then you trigger a flow from ADS4 to ADS2, and you can do localization, microstate counting, and everything you want. You can take the Riemann surface to be a sphere, to be an hyperboloid, to be a spindle, which are solutions that are these days under investigation very actively. But then you can also place it if you want in type 2b, and in that case you will have an S-fold CFT3 placed on a Riemann surface with a topological twist, and then the Riemann surface could be whatever you want, and then you can ask yourself how the whole story about localization, etc., how it works in this type 2b. So just to conclude, maybe a bit too early, so maybe just to conclude, let me just show you the email we got from the referee report we got about the paper. And actually, if the person is in the room, so thanks, because we were very happy about the report. So the person said that this paper establishes very non-trivial new results. Actually, very non-trivial is it's very nice, because only non-trivial would have been enough, but very non-trivial is even better, right? So this paper establishes very non-trivial new results that could be important for the SCFT correspondence. And I just want to say that I agree with the referee report. So, thank you. No, I'm not making a joke. It's like, I think this result can be useful for holography.
For questions?
Yep. This is good. This is a very nice question. So, as we heard this morning, whenever you have pure supergravity, as this is the case I'm talking about, this is pure n equals 4, d equals 4 supergravity. So essentially this, on the gravity side, just having the supergravity multiplet amounts to just having the stress energy tensor in the field theory, right? So then, what I'm saying by this is that the fact that n equals 4, d equals 4 supergravity can be embedded in 11D or in type 2b, to me, means that this stress energy tensor dynamics is sort of universal. So I can place it in AVJM, or I can place it in type 2b. Of course, I could start with n equals 4 supergravity and now put vector multiplets. That could be flavors in the field theory. And then, type 2B or 11D, AVJM, or the S4 CFTs, they could have different possibilities for flavoring them. So somehow, to me, just retaining the pure supergravity multiplet is just capturing sort of like the universal part of three-dimensional conformal field theories with that amount of supersymmetry. So it's like, to my taste, it's like if you take AVJM and you take these S4 CFTs, the intersection is going to be the stress energy tensor, and it is precisely this n equals 4, d equals 4 supergravity, which is, as you said this morning, is not only gravity, it's gravity coupled to a complex scalar and 6 vector fields, which is what you need for the stress energy tensor, because you need the R-symmetry currents and so on. So for me, this is the reason why you can embed this thing into the two theories, because it's sort of the universal piece. It's like the intersection of the two CFTs. They are different, and that's why when you take AVJM, for example, take AVJM and write it using n equals 2 supermultiplets, as people normally do. If you do that, then there will be an exact U1 symmetry, and the rest is going to be flavor symmetry. If I do the same with the S-fold, there will be an exact U1 symmetry, and the rest will be flavor symmetry. And what I'm saying is that the completion, so essentially all the flavor part is different from AVJM and from the S-fold CFTs. Different superpotentials, different superpotentials in the field theory side. Different superpotentials, different global symmetries in the field theory sides. But as long as I attach to the R-symmetry part, that block is universal, and this is the one captured by this. So there will be scalars and so on describing fluctuations, which are flavor-like fluctuations, and those will depend on whether you went through the 11D road or you went through the type 2B road. I don't know how will they behave. I don't know. So finite n, you mean, I don't know how the finite n effects will be similar or different in the two setups. I don't know. Also because in the S-fold, so in the same way as if you take the M2 brane solution in supergravity, in 11D supergravity, you take the near horizon geometry, and then you get the ADS4 crosser 7. If you ask me whether the same is known for the type 2B thing, like is there a brane setup such that if I take the near horizon geometry, I end up in the n equals to 4 S-fold in type 2B supergravity? It's not known. So really like 11D supergravity and AVJM, they have been like super studied in the last 25 years, but this type 2B alternative is new. I mean, it's completely unexplored, and there are essentially an infinite number of open questions, I would say. That's a good point. So type 2A, if I go to the massless type 2A, then it's the same as going through 11D. But if I go through the massive type 2A, then let me start differently. If I'm in 11-dimensional supergravity, I know that I can take 11-dimensional supergravity, I can place it on the 7 sphere, and then I get an n equals to 8 maximal supergravity of the Vitan Nicolai, and this n equals to 4 is a subspace. It's just some subset of the fields. If I start in type 2B, I place it on S1 cross S5, I get a maximal supergravity, and I know that this n equals to 4 is a subset of the fields, and it is a consistent subset because we prove it. If I take massive 2A, and I place it on the 6th sphere, then I get a maximal supergravity, and that maximal supergravity does not contain an n equals to 4 vacuum. So in principle, it's not a priori guaranteed that massive type 2A, according to Gauntlet et al. Conjecture, that there will exist a consistent truncation of massive type 2A on the 6th sphere to this n equals 4, d equals 4 sector. It might exist, but there is no... Yeah, but that question depends on who you ask, right? In principle, yeah, but think of, for example, in the field theory side, people show that if you take massive type 2A and then you place it on CP3, you end up in AVJM. But now, if you allow the Chern-Simons levels to not to adapt to 0, then the difference between the two levels, K1 and K2, is precisely identified with Roma's mass. So people would somehow say that there is a relation between, at least holographically, there is a relation between 11D and massive type 2A, which is taking AVJM and essentially make the two Chern-Simons levels. It's a bit indirect. Yeah. It's a bit indirect. But yeah, well, I agree, it's a bit indirect.
You gave a particular example, like, I mean, for like the for before dimension. Do you think, I mean, this phenomenon can be like more generic?
Yes, it can be more generic, and actually we are working also on that. So there is also a way of using this exceptional field theory and this generalized notion of G structures. This is the simplest example, but there is a way of working out consistent truncations, not only to pure supergravities, but also to supergravities coupled to vector multiplex, and we are matter multiplex, and we are working on that at the moment. But it's extremely technical, so I didn't even want to mention.
Speaker. I should not use. And I have already downloaded here, but I should not use this. It's fine.
That should be fine.
Okay, so the next speaker is Fiona Seibold. She's going to tell us about integral deformations of ADS3 strings. Please.
Thank you. And yes, thank you to the organizers for organizing these very nice workshops and for giving me the opportunity to present this work. So the motivation behind this work is similar to what we have heard yesterday during the talk by Sibylle Driesen, and it comes from ADS-CFT. And as you have heard several times now, I guess the most studied example of this correspondence is between type 2B superstrings on ADS5 cross S5, and on the CFT side we have n equal 4 super Young Mills in 4-dimensional flat space. And in some limit, so namely the one of free strings on the string theory side, and in the limit of planar graphs for the dual CFT, these models become integrable. And integrability then allows to do a lot of calculations in order to compare data on each side of the duality and provides further tests of this correspondence. And given this success, one can then ask whether there are other types of setups, ADS-CFT setups, for which this integrability program can be applied, so that also in these setups we can try to obtain a duality and compute observables on both sides of the correspondence. And there are different ways of approaching this problem. So one of the ways is to look at lower dimensional ADS-CFT setups. So instead of considering strings on a background with an ADS5 factor, can go lower in dimensions. For instance, strings with an ADS4 factor or ADS3 or ADS2. And the lower you go in dimensions, which is also the theme of this workshop, well, the less supersymmetries you will have, and there will be new features appearing that would be very interesting to look at more carefully. In particular, in this talk, I will focus on the case where there is a 3-dimensional ADS space. And this is something that has been looked at, especially by Linus Wolf in a set of papers, where he tried to classify all backgrounds, all type 2B supergravity backgrounds that contain such an ADS3 factor. And he did it for so because we are in supergravity, we want to have a 10-dimensional spacetime, so we should complement it with some spaces. And he looked at all the solutions in case where this M is a symmetric space or a product of symmetric spaces. And he found something like 11 solutions for type 2B supergravity. Then there are also many types of integrable backgrounds that one can construct that also contain these ADS3 factors, and many people in the room have worked on that. And then Linus Wolf also looked at the overlap between these two sets of theories. And remarkably, there are only very few such theories that contain both an ADS3 factor and that are constructed using symmetric spaces and that preserve the integrability of the model. And they are listed here. So these theories will actually preserve some amount of supersymmetry. So you might be familiar, for instance, with ADS3, S3, S3, S1, which has 16 supersymmetries, which is half of the one of ADS5 cross S5, and similarly also ADS3 times S3 times T4, which also has 16 supersymmetries. But then there are also these other solutions which contains 2 spheres which have less supersymmetries, namely 8 supersymmetries. So this is a way, so in principle, also these theories should have some CFT dual, and therefore it's interesting to look at these theories in more detail. And another way that one can proceed in order to find other examples of ADS-CFT setups where integrability plays an important role is to look at integrable deformations. So starting from an integrable theory and engineering some deformation such that integrability is preserved, but such that one has a family of theories that depend on some continuous deformation parameter, and so that the whole family of theory is actually integrable. And these type of deformations, they were considered also yesterday in the talk by Sibylle, so I will review some of them here. So namely, we have the so-called TST transformations. For instance, in the case of ADS5 CFT4, on the string theory side, there is this Lunin-Baldacena background, and the dual theory is known, this beta deformed n equal to 1 theory. And there are also these Jordanian deformations that were focused on yesterday. And in general, in the context of holography, these type of theories are expected to be dual to some non-commutative theory. All these, so these TST transformations and these Jordanian deformations are special cases or what is called homogeneous Yang-Baxter deformations, and they correspond to some twisting of the boundary condition or of the symmetry algebra. So a way to phrase this is that this theory on a deformed background, you can also, with periodic boundary condition, you can also see it as some undeformed, so a theory on an undeformed background, but with twisted boundary condition, and the symmetry algebra will get twisted. There is another class of deformation that has not been mentioned so far, I think, during the conference, which are these inhomogeneous Yang-Baxter deformation. And in that case, instead of having a twisting, so this will really modify the geometry locally, and in practice there will be the quantum group deformation. So the algebra gets promoted to a quantum group. And there are 2 types of solutions, namely the eta deformation when this parameter in the quantum group is real, and also the lambda deformation when this parameter is a phase. And many people in the room have worked a lot on this type of theories. So this was the two directions in which one can go in order to explore more ADS-CFT setups. And in this talk, I will combine them and look at some deformations of ADS3 strings. So I will start from ADS3 times S3 times T4 in particular, but most of what I will say can be generalized also to ADS3, S3, S3, S1, and in some cases I will make precise remark on that, and then look at some deformations that will preserve the integrability of the model. There are, of course, many such deformations, as I've just highlighted. So in this talk, I will also focus on these deformations that preserve some amount of supersymmetries. In practice, we will have usually 8 supersymmetries that are preserved. And this is work that is based on some various works, but mostly together with Ben Hoare, Anna Rettore, Alessandro Sfondrini, also Arkady Zeitlin, and some of them are in the room. All right, so let's start with some examples of TST transformations, which are arguably the simplest type of deformations that one can do. So, but first of all, in order to tell you exactly how these deformations work, I should say something about the undeformed theory. So just ADS3 times S3 times T4. And the reason why looking at ADS3 is interesting is that the three-dimensional sphere and the three-dimensional ADS, they are symmetric spaces, but they are also group manifolds. And this will allow us to define a lot more integrable deformations than in other setups, for instance, ADS5 cross S5. And these bosonic symmetries, so for the sphere, these 2 copies of SU2, and for the 3-dimensional ADS space, these 2 copies of SU1, in the superstring action, so when adding fermions and having supersymmetry, this will gather into 2 copies of this PSU1, /2 superalgebra. And this is where these 16 supercharges come from. 8 from the left copy, and in total there will be 16 supercharges. And so here now I want to do this TST transformation that is, in some sense, the simplest type of deformation that one can do for these backgrounds. And this type of TST transformation can be done for any background that has at least 2 U1 isometries. And the way it works is that assume that these 2 U1 isometries are realized through shifts in the coordinates phi1 and phi2. So this TST transformation is a combination of T-duality in this coordinate phi1, where you T-dualize, and you go, for instance, from type 2b to type 2a. And then in the dual theory, you do a shift of the other coordinate with some parameter beta that involves the T-dual coordinate phi1 tilde. And then one T-dualizes back to the to type 2b, and does the T-duality again in this coordinate phi1. So this, in general, it will map supergravity solutions to supergravity solutions. So what can be done in the case of ADS3S3T4? So here I rewrote the bosonic symmetries for the ADS3S3T4 string. So there are the 2 copies of SU1, coming from ADS3, and the 2 copies of SU2 coming from the 3-sphere. And here there are also the 4 U1s from the T4. And of course, there will be 4 U1s sitting in these SU1, and SU2 groups. And therefore, one can use these U1s in order to do TSTs along any of these directions. So here, I would like to preserve some amount of supersymmetry. So I will choose to leave the left copies always invariant. I don't want to deform them. So I will not touch the U1 left from SU1, left, or the U1 left from SU2 left. I will just play with the right copy or the U1s in the torus direction. So the first thing that one can do is to take 1 U1 from the sphere and then 1 U1 from the torus direction. And what happens to and do the TST in those directions. And then what happens to the background, so this is something that has been looked at quite some time ago. And what happens is that, of course, because we didn't touch the U1s from ADS3, the ADS3 factor is still there. However, there will be now a squashing of the sphere with this parameter delta. So here, so this is the metric of the sphere. So if delta equal to 1, this is the metric of the sphere written in Hopf coordinates. And after the TST deformation, there will be some squashing of the sphere where you recognize the metric of S2. And here, this would be the Hopf fiber. And the relation between the TST parameters, so the shift in the TST, and the squashing here of the sphere is through this formula, and delta takes values between 0 and 1. And delta equal to 1 is just the sphere, and then we will see also that something interesting happens when delta equal to 0, which corresponds to the maximal deformation limit. So here, this is for the metric. Then one can also work out what happens to the dilaton and the fluxes. Remarkably, so the fluxes are quite simple. They just are some combination, some linear combination of F1 and F2, where F1 is just the standard volume forms, and then F2 involves the fiber AES. And the dilaton remains constant, and I set it to 0 for convenience. And so, as I mentioned, there is some interesting limit that happens when this delta parameter is taken to be 0. Of course, one needs to be a bit careful in how this limit is taken in order to not run into divergences. And if one does that carefully, then there is some flat direction that appears, and the S3 part basically breaks down into just S2 and the flat direction. And similarly, one can play the same game for the dilaton and the fluxes, and one gets this result. And if one compares with the results obtained by Linus Wolf, then one sees that this is actually the ADS3 times S2 times T5 background. So the conclusion of this is that this type of deformation, this TST transformation, allows one to interpolate between this solution, this integrable solution, ADS3 times S3 times T4, which has 16 supersymmetries, and this ADS3 times S2 times T5, which has 8 supersymmetries, and so for the whole family of background that interpolates between these two solutions, one preserves 8 supersymmetries. So this is something that preserves integrability and preserves 8 supersymmetries and allows one to go from one background to the other, and has some geometry of a squashed sphere. One can play a similar game in the case of starting from ADS3 times S3 times S3 times S1, and this is in some recent work with Alessandro Sfondrene. And one can go from, for instance, from this background 1 to 2 or 1 to 3. Now, a remark is that in order to do this TST transformation and do this interpolation, we use the, so it's important to use the start from the pure Rameau background for ADS3 times S3 times T4. One can, of course, start from the mix. So, yeah, if you're not familiar, ADS3, S3, T4 can be supported by several fluxes. It can be pure Rameau or pure NS-NS. In that case, you have a CFT. Or it can also be something that is mixed flux, where you have both Rameau and NS-NS fluxes. And here, all what I said, all the formulas that I've wrote are valid when starting from the pure Rameau background and doing TSTs there. But one can, of course, also start from the mixed flux case. But what happens in that case is that it's not possible to interpolate all the way to S2, for instance. So the amount of NS-NS flux will put a lower bound on the squashing of the sphere that one can do. Yeah.
In the cases where you have, like, let's say case number 3.
Yes.
Are the sizes of the two spheres independent, or how are they related?
Yes, so there will be a radius of ADS3, there is a radius of S2. So here, no, here they are fixed. So it's only in that case where there will be some freedom.
Okay, but in case 2 and in case 3, these radii are like the sphere radii.
Sorry. So there is a relation, there is one relation between the 3 radii in all 3 cases. In all 3 cases, yes. One relation. So it's
Freedom of, like, changing.
so there is only one relation, yes, and it's you can see it from having this parameter alpha still in the symmetry algebra. Yeah. Yes, so you can start from for instance, this one, and taking the decompactification, you land on case number 4, and similarly, if you start from this last one, and take the decompactification, you land on the case number 5. Yeah. Mm-hmm. So no, I do not understand it. This is one of the open questions. Yeah, this is very interesting because they preserve the ADS3 factor. So in principle, they have a CFT dual, but I do not know what this would mean for the dual theory. But this is an open question, I think. Mm-hmm. Okay. So all what I said is really treating T4 and T5 as R4 and R5. I do not really look at the precise topology. Sorry. So for S3, yes, for S3 the E2 is going to S2. But for the torus direction, it's I treat the coordinates as being just flat directions. So the decompactification limit from these 3 cases to these 2, or no, this can be taken nicely. There is no problem there. Okay. So this is, I showed the case where one U1 is taken from the curved geometry and one U1 is taken from the T4 geometry, but one can also do take a U1 from ADS3 and the U1 from the sphere. However, now the difference is that I will be touching the ADS3 factor. And the result is the following. So it will be similar as before. There will also be a squashing of the sphere, but now also the ADS3 part will be deformed, and there is some warped ADS3. Now, compared to the talks that we have heard previously in that case, I'm not sure exactly how it links to those, but in that case, the warp factor is really a constant. And the relation between the shift parameter and the warp factor is similar to before, except that now this delta is positive. It's not between 0 and 1. Again, one can work out what happens for the dilaton and the fluxes, and similarly to before, what happens is that there will be linear combinations of these two three forms that appear, where again F1 is the volume, the standard volume form, and F2 involves the fibers. One can do an analytic continuation. So because this delta was now positive, this prevents us from going, for instance, from S3 to S2. But one can do an analytic continuation. And in that case, it is possible, again, to use this type of TST transformation in order to interpolate between something that has an ADS3 factor and something that has an ADS2 factor. So for instance, one can go from ADS3 S3T4, which corresponds to delta equal to 1, and something that is ADS2 times S2 times T6, where delta is equal to 0, in a similar way to what I showed previously. The boundary. Which boundary would that be? Yes. It's some warped ADS3 geometry in between. The dimensionality? Yeah, if one wants to do holography, then it would no longer be a CFT2. There will be some CFT1 sitting in there, but it's not clear to me exactly what it means in terms of holography. I mean, all of these backgrounds, I think there is a lot of potential to understand them from the point of view of holography. I'm not sure if there are really concrete answers so far. Mm-hmm. No, I mean, in that case, there won't be any CFT2. Yes, also, yeah, for ADS3, holography is not completely understood, especially for this background, which have Ramon-Ramon fluxes. So this was one type of deformation that one can do, which are these TST transformations, which are very useful to interpolate between non-integrable backgrounds. And another type of deformation that I want to mention here are these Yang-Baxter deformations. So this is the action. So this Yang-Baxter deformation is a deformation of the sigma model description of the theory. And we have seen already the action in the talk of yesterday, but this is to remind you of its form in the simplest case of the Yang-Baxter deformation of the principal chiral model. So you take the principal chiral model, which is just a trace of some left invariant Maroy-Caton forms, G inverse dG, where G is some group element. And in between, you plug in some operator that depends on the so-called R matrix or operator R. And in order to preserve, and eta is some deformation parameter that allows you to So eta is equal to 0 is just the undeformed PCM, and eta different from 0 allows you to go away from the PCM. And to preserve integrability, there are constraints that this operator R needs to satisfy. One of them is that it needs to be antisymmetric, and then it also needs to satisfy the classical Yang-Baxter equation. So this classical Yang-Baxter equation can come in different forms, depending on what you have on the right-hand side here. So yesterday we mostly saw the case where C is equal to 0, which is the standard classical Yang-Baxter equation. This is the homogeneous Yang-Baxter deformation, and these TST transformations are just a special case of that. So in all these cases that I described, well, at least the one where you just act on the curved part of the background, you can find the operator R that generates these TST transformations. And then you can also do something more, in particular these Jordanian deformations. But you can also consider the case when this right-hand side, so this is non-vanishing, which is called the modified classical Yang-Baxter equation. And this is a model that will still preserve the integrability. It will still preserve integrability. And this is called inhomogeneous Yang-Baxter deformations or eta deformations. Here in this talk, I would like to focus on solutions to the modified classical Yang-Baxter equation. And a particular solution of this type of equation is the Drinfeld-Jimbo solution. So the way it is constructed is that you take the Lie algebra associated to this Lie group G, decompose it, so choose some Cartan-Weil basis with some Cartan generators, positive and negative roots, and this operator R annihilates the Cartan generators and multiplies with plus or minus I the positive and negative roots. And this can check satisfies this modified Yang-Baxter equation. In general, this type of deformation, so it will only preserve the symmetries generated by the Cartan elements, and in general, all the supersymmetries will be broken. So this would be for the manifest symmetries, but there is actually a hidden quantum group symmetry. So you've never seen a quantum group, so this is how the commutator between elements would look like in the Q-deformed theory, where A is the Cartan matrix for the Lie algebra G. And what happens is just that the commutator between positive and negative roots gets modified. Instead of having just a Cartan element on the right-hand side, you have some combination that involves this parameter Q. And for this type of deformations, this inhomogeneous Yang-Baxter deformation, this Q is real, and it's related to this deformation parameter eta in the action. So now I want to focus on the case of ADS3 S3T4, and in that case, the Lie algebra that one needs to consider is given by two copies of PSU 1,1/2, and therefore one can deform each copy separately. You don't need to deform both copies. You can just deform one copy with some parameter Q left, and the other copy with some parameter Q right. And this will allow you in particular to just deform one of the two PSU 1,1/2. A remark is that in principle, in order to make sure that after deformation, so this deformation is engineered such that the integrability of the model is preserved. But if you want to have an interpretation in terms of string theory, you would like, for instance, that your deformed background also solves the supergravity equations. And as we have seen yesterday, this imposes an additional constraint on the operator R, and this is this unimodularity condition. And one can show that there is no problem in that case. One can find a Drinfeld-Jimbo solution such that this unimodularity condition is satisfied. And as I said, it depends on the Cartan-Weil basis, and one just needs to take the Cartan-Weil basis of PSU 1,1/2, where all the simple roots are fermionic, so associated to this thinking diagram. And this will ensure that the deformed background also solves the type 2B supergravity equations. So here, as I said, one can deform the two copies independently, and since I want to preserve some supersymmetries, let's look at the case when we just deform the right copy of PSU 1,1/2 and leave the left copy invariant. So this is, you plug in the Yang-Baxter action, and then read out the metric and the fluxes, and this is the result. So the the metric is actually very similar to what we have already seen for one of the TST transformation, namely there will be a squashing of the sphere and also a warp ADS3 factor in the geometry. Can also obtain the dilaton and the fluxes in that case, and again it is some combination of the volume form and of the Hopf fibers. So what is interesting in that case is that you actually obtain the same metric as the TST transformation. However, the fluxes are different. So I remind you that for the TST transformation, we had these fluxes. And now for the Yang-Baxter deformation, instead of having H3 and F3 turned on, we have F3 and F5 turned on. And these TST and Yang-Baxter fluxes are related through, one can check that they're related through some T-duality in the torus direction, and additionally some S-duality rotation between H3 and F3. So this is kind of very similar to what there is also in the undeformed theory, where one can have this mixed flux theory, which preserves the integrability not only for pure Ramond-Ramond, but also for this mixed flux theory. And the same thing happens here, where this type of rotation between H3 and F3 preserves the integrability of the model. And another thing is that because we only deformed the right copy, this is an example of inhomogeneous Yang-Baxter deformation that actually preserves some amount of supersymmetries, namely 8 supersymmetries. A note is that this type of deformations are also closely related to so-called lambda deformation, where Q is no longer real, but it's a phase. And also in that case, this is something that has been looked at by people in the room very recently. Also in that case, it is possible to find some backgrounds that preserve some amount of supersymmetries, 8 supersymmetries. And these type of theories are related to through so-called Poisson-Lie duality. And there is a whole web of duality that I think still needs to be explored. All right, so this was for the Yang-Baxter deformation, and now let me come to the last type of deformation of ADS3 strings that I will consider, namely the elliptic deformation. And this deformation really relies on the fact that ADS3 and S3 are both coset spaces, but also group manifolds. So the bosonic theory, at least when just looking at bosonic strings, you can find it's described by the principal chiral model. And now I will change the operator that appears here. Instead of having something that depends on this Drinfeld-Jimbo solution, I will have some other type of operator which acts as follow on the 3 generators of SU1, 1 and as follows on the 3 generators of SU2. So it would be a squashing of the sphere, but in all 3 directions. And there are 3 cases. So one is when all these deformation parameters are equal. This is just a rational case. And there is, for instance, for the sphere, there is the SU2 left times SU2 right symmetry. Then there is the trigonometric deformation, where 2 of these deformation parameters are equal. And then, so the left symmetry is always preserved because it's constructed using the left invariant Majorque-Cartan forms. But this breaks the right symmetry down to just U1s. And this is actually the Yang-Baxter deformation that we just looked at previously, up to some closed B field. And the deformation that I want to look at now is the elliptic deformation, which is one step further and deforms all 3 directions. And in that case, there is not even the U1 that is preserved. So the elliptic deformation is classically integrable. So as for the TST and as for the Yang-Baxter deformation, at least for the bosonic theory, one can obtain a Lax. The equations of motion of the theory are equivalent to a flatness condition. As I said, the trigonometric deformation is related to the inhomogeneous Yang-Baxter deformation that I just mentioned previously. Both the rational case, which is just the end-deformed theory, and the trigonometric deformation, so this Yang-Baxter deformation, can be generalized to supercosets to describe superstrings. However, for elliptic deformations, this is something that is not known yet how to do. So we don't know yet how to write down a sigma model. that would give rise to deformed ADS3 superstrings, elliptic superstrings. And we also don't know, in principle, if classical integrability, so the integrability of the Lux type, persists at the quantum level. However, one can actually make some progress by using the bosonic theory, which we know to be integrable, and try to embed it into type 2b supergravity. And the guiding principle is to preserve as many symmetries as possible. So deform the ADS part of the geometry and the sphere in the same way, and then use only left invariant field binds, and then do some ansatz for the fluxes. So construct some auxiliary fluxes using these field binds, and then postulate that the fluxes are some linear combination of these auxiliary three forms. So this is motivated a bit from the observation of the TST transformation and of the Yang-Baxter deformation. And then, so these x1, x2, x3, x4 are some vectors of parameters, and imposing that the supergravity equations of motion then imposes constraints on the norm and on the scalar product of these vectors. But there is a solution. So it is possible to embed the bosonic geometry into type 2b supergravity. And in fact, one can check, and this is work in progress with Ben Hoare, that this background actually preserves 8 supersymmetries if one imposes some additional constraints on these vectors. So also in this elliptic deformation, it's possible to preserve some amount of supersymmetries. All right, so I mentioned at some point that these models are integrable, at least at the classical level. So let's look now at quantum integrability, and the way this is done in integrability methods is to look at the worldsheet S matrix. So as you have seen yesterday, I think, so you start from the sigma model, or from your sigma model description of the theory, and then you need to fix some redundancies in order to have a theory that is defined on the worldsheet that is of the form of a cylinder, and then you take the decompactification limit where the cylinder becomes just a plane, and on this plane asymptotic states are well defined, and you can look at the scattering of excitations. And for an integrable theory, at least in the standard types of integrable theory, for massive excitations, integrability, so the conserved charges behind integrable models will impose restrictions on the type of scattering that it's possible to have, and this is represented through this Yang-Baxter equation, which are the different ways in which a three-body scattering event can be decomposed into two-body scattering processes. So if we want to check the integrability, the quantum integrability of our theories, the way to go is to do this procedure, compute the S matrix, and check that Yang-Baxter is indeed satisfied. So maybe a technical thing that also has been addressed yesterday is that for these deformed theories, usually the symmetries that are preserved do not allow to do the usual Lycon gauge fixing. So the usual PMN geodesics, which is just a point-like string propagating in time in ADS3 and in some great circle on S3. This is no longer a classical solution, so we need to adapt a bit around which classical solution the theory is expanded. And this is this alternative Lycon gauge fixing. And here the symmetries that are preserved are the ones that we didn't deform, so the U1s coming from the left copy. So this is just some technicalities about how the Lycon gauge fixing is done. So we will define Lycon coordinates that now only depend on the left Cartan elements, xi left of ADS3 and zeta left in ADS3 and xi left in S3, and then fix so-called uniform Lycon gauge where x plus is fixed to tau, and the conjugate momentum, the momentum conjugate to the coordinate x minus is taken to be a constant. Then solving for P plus then gives the Hamiltonian of the theory, which usually has a very complicated expression. And a way to proceed is to look at some perturbative expansion where H will have some quadratic piece, and then we can perturbatively quantize the theory. So this is also the approach that was taken yesterday. So here I will focus on the elliptic deformation. And in that case, by doing this Lycon gauge fixing procedure, at the quadratic level, one lands on a non-relativistic theory for 8 excitations, so 4 of them coming from bosonic excitations and 4 of them fermionic excitations. And also, as for the Jordanian deformation of yesterday, we have this funny double square root structure between the energy of the excitation and the momentum of the excitations. And here, gamma 1, gamma 2, and gamma 3 are deformation parameters. So for the bosonic excitations, these deformation parameters are directly related to the deformation parameters in the action, this alpha 1, alpha 2, and alpha 3. Also here to make sure, so I deform ADS3 and S3 in the same way, so I only have 3 deformation parameters. And then for the fermionic excitations, there is a similar type of dispersion relation with double square root form, but now, so these will depend on the parameters in the fluxes, and if you impose this additional constraint to have supersymmetry, there will be a matching between the dispersion relation and between these gamma 1, gamma 2, and gamma 3 deformation parameters. So in that case, in our case, we're lucky. There are no cubic interaction vertices, so we can go ahead and just look at the quartic interaction vertex. And from this quartic interaction vertex, we can read out what is the 2-to-2 scattering in our theory. So we can obtain the 3-level S matrix and then check whether this is consistent with the Yang-Baxter equation. And what we find is that actually this is completely fine. The 3-level S matrix that we obtain in this elliptic deformation is actually compatible with the Yang-Baxter equation, at least to the order that we can check. So we only do the expansion of the Green-Schwarz action to quadratic order in the fermions. So we can only check, we cannot check processes that involve 4 fermions interactions, but all the other types of interactions, they seem to preserve this, the Yang-Baxter equation, at least when we focus on the solution preserving some amount of supersymmetries. So also this type of theory seems to be, this elliptic deformation seems to be integrable. So here I presented the methods to obtain the perturbative S matrix. In principle, for integrable theories, there is also a method to obtain the exact S matrix. So this 3-level S matrix would just be the first term in the expansion to all loop orders. And the way this is done in integrable theories is that this exact S matrix is bootstrapped using the symmetries of the theory. So this S matrix should preserve the symmetries, for instance, for ADS3, or at least of the Lycon gauge fixed theory. And what happens for these homogeneous Yang-Baxter deformation, in particular for TST transformations, in principle, this S matrix of the deformed theory should it should be possible to obtain it from the undeformed theory by dressing it with some Drinfeld twist, which needs to satisfy some co-cycle conditions so that Yang-Baxter equation is automatically satisfied also for S prime. There might be some subtleties when this twist also involves the Lycon direction, so the one that we use for Lycon gauge fixing, and this has been addressed in this paper. For the trigonometric deformation, which actually corresponds to this inhomogeneous Yang-Baxter deformation, we can also exploit this quantum group symmetry, which is hidden, but it's still very powerful in order to constrain the Welschitt S matrix, and also in that case, it's possible to write down an exact S matrix, at least up to dressing phases, where one needs to impose additional constraints in order to obtain those. In the case of elliptic deformations, well, we don't know yet. We don't know what the exact S matrix would be, also because we don't know what happens to the symmetries in these theories, and we actually don't even have a sigma model description of this theory. for the superstring. So let me come to the conclusions and also some open problems. So what I try to convince you in that talk is that there is a very rich space of integrable deformations of ADS3 strings. Some of them preserve some amount of supersymmetries, so 8 supersymmetries. They can interpolate between known integrable backgrounds. We also constructed some new type of elliptic deformation of the ADS3 S3T4 superstring. So the space is very rich, and actually it has not been completely explored yet, so there is a lot of things to do there. And for this elliptic deformation, we have checked that at least the tree-level S matrix is compatible with integrability. So there are a lot of open questions. So one of them is related to this elliptic deformation, where we suggested some supergravity embedding, but as I said, we don't have any sigma model constructions. It would be very nice to see whether the methods that were also discussed yesterday can be used in order to construct this type of deformation in a systematic way. Another open problem is what happens to the symmetries in this elliptic deformation, and what happens to the exact S matrix. For instance, whether it is related, so there has also been work in looking at the S matrix, like trying to bootstrap it, not using the symmetries, but just by brute force solving the Yang-Baxter equation, and there have also been some proposals for some type of elliptic deformation, and whether there is any relation between this type of S matrix and this elliptic deformation is unclear yet. Another aspect is what happens in the mixed flux case. So most of what I said was for pure Ramond backgrounds, but in principle, these Yang-Baxter deformations, it's possible also to add a Wess-Zumino term, which also preserves the integrability of the model. However, also in that case, an exact S matrix is not known yet. So that's also an open problem. And also, what is the meaning, whether it's possible to obtain these deformed geometries from some brane setup. This is also an open problem. And also, of course, we had also many questions about this, about the interpretation of this type of deformation in the context of holography. So there has been a lot of recent work on ADS3 CFT2 duality, mostly for NS theories, but also trying to go a bit away from that. And some of these theories, especially the ones coming from TST transformation, they preserve the ADS3 factors, so there should be some CFT2 dual, but it's not clear what those are. And also for the theories where even ADS3 is not preserved, where there is this warped ADS2, also what is the interpretation of those? Also, that also was something that we've heard in the talk by Monica Gueca this morning. And also, so those are, I think, very interesting questions, and I will let you reflect on those. Thank you very much. Yes, so here I only focused on the case where I always did one TST transformation, but one can, of course, also do consecutive TSTs, and then you will generate multi-parameter deformations. So this is something that is possible, yes. In general, this will give rise to more complicated geometries, of course. So here I focused on just having one TST because I wanted to have these nice interpolating backgrounds. And if you have multi-parameters, it will be something that is much more complicated. That's probably possible, yeah. It would be interesting to look at that, yeah.
όχι, είπαμε να βάλουμε το τέτοιο για να μην χάσουμε... έχω το τέτοιο εδώ, το ηχείο.
Το βγάλουμε σιγά σιγά.
Ωραία, για να βγάλει το άλλο.
Μόνο που θες τέτοιο, να σου πω.
Δεν έχει.
Αυτό που δεν μου είναι προφανές.
Οκ, για να δούμε.
Θα παίξει με τη ROM, αλλά τι να νοιάζει, αφού αυτό φαίνεται ότι θες το έτσι. Άρα, εδώ, το πρώτο.
Αυτό ναι, αυτό κάνει.
Αυτό είναι το... Δεν κάνω τίποτα εγώ προς το παρόν. Εγώ δεν κάνω τίποτα. Εγώ ας να κουμπώσουμε αυτά που κουμπώνουμε. Να κουμπώνουμε αυτό. Αυτό φαντάζομαι ότι μπορεί να μπαίνει και στον υπολογιστή σου. Δεν αποκλείεται να μην έχει. Βασίλη, να το.
Α, έχει. Δεν το ξέρω. Α, είναι τα ακουστικά, ρε. Ναι, ναι, δεν το υπάρχει.
Τα χρησιμοποιεί κανένας. Αυτά δηλαδή.
Identifying your keyboard.
Πάτα απλά ένα...
Cannot be identified.
Εντάξει, δεν πειράζει. Απλά κλείστο και θα το πάρει.
You have pressed a key on your Apple. Please press the keys on the keyboard that can be. What?
Εγώ νομίζω ότι το escape να πατήσεις και να το κλείσεις θα δουλέψει μια χαρά. Κλείνει αυτό. Αν πατήσουμε το back και quit,
Το έκανα.
quit. Τι, εντάξει, βάζεις quit.
Όχι, πρέπει να κάνω...
Mirror.
Mirror, εδώ το τέτοιο. Choose content. Αυτό. Mirror this window.
Εντάξει.
Continue to mirror. What? Α, το έχεις το άλλο.
Ναι, εγώ θα αλλάζω. Απλά να πάρει το cursor, αν μπορείς. Αν μπορείς πάρει το cursor. Πού είναι το cursor, κάπου είναι. Πέταξε εδώ πάνω. Στο διάταμο. Βασίλη, μόνο επειδή αγχώνομαι λίγο.
Ναι.
Να το σπρώξουμε λίγο προς τα μέσα.
Ναι, παίρνουμε
Γιατί
το
αγχώνομαι
εδώ.
αγχώνομαι πως πέσει κάτω.
Με Wall Street. Wall Street. Οκ, εντάξει, νομίζω είναι fine, ναι. Νομίζω πρέπει να είναι...
Και Wall Street, εσύ τέτοιο. Τώρα δεν θα χαθεί καμία εξίσου. Όχι, δεν μπορεί να κάνει τίποτα. Είναι σαν να κάνει sensory ο τέτοιος.
Ο Bill Gates. Οκ, εντάξει, fine.
Τι άλλο, ρε, τι κάνει η Μαρία.
Καλά, ωραία, εντάξει. Εσείς όλοι καλά εκεί.
Πώς χαίρετες όμως.
Ευχαριστώ.
Τα κορίτσια.
Εντάξει, μεγάλο τώρα είναι μεγάλη ιστορία του εγώ. Κοντεύει να τελειώσει με το σχολείο.
Πώς είναι 17.
Όχι, όχι, και μικρή. Πόσο καλύτερα, 15 πόσο. Οπότε έχουν βγει μέσα.
Στο σχολείο αυτό το διεθνές.
Ναι.
Και μετά.
Μετά δεν ξέρω, να σου πω, πώς πάει στο εξωτερικό.
Πώς είναι ρωτήσεις οδήγηση Παναγιώτη.
Όχι, δεν οδηγεί, ίσως, δεν ξέρω, κάτι να κάνουν τώρα, να βάλουν όλα αυτά. Το ξέρω, ναι, μα βάλανε αυτή τη λίστα με τα πρώτα πάγια από μπακαλάρες, και αυτό που είναι δημόσια δεδομένα.
Γιατί, να σου πω κάτι, υπάρχουν κάποιες σχολές στην Ελλάδα που ίσως φέρουν.
Ναι, δεν πρέπει να είναι και Δεν κάνουν τίποτα. Μεσοπαίζουν δηλαδή. Είναι γραμμένη εκεί, γραμμένη στο άλλο. Θα τους εξετάσουμε πάρα πολύ.
Αυτό εδώ πέρα έχουμε δυνατότητα. Υπάρχει καλά. Μα είναι έτσι. Αλλά δεν έχεις κάτι το πάνω εδώ. Πόσο μακριά πρέπει να είμαι?
Πιάνει αυτό, μια χαρά.
1, 2.
Ήδη έχεις δυνατή φωνή.
Το θέμα είναι να ακούγεται στα... Το κάνετε stream.
Εντάξει, μέχρι εδώ νομίζω.
Εντάξει, ας το νόμιζα, ας το νόμιζα. Εντάξει, θα κάτσω εδώ πέρα.
Γιατί έτσι και στο βάλω αυτό. Το βάζεις αυτό και το βάζεις στο πέτρο, κατεβάζεις το
Θα το δέσουμε εδώ πέρα. Ωραία, ωραία, οκ. Ναι, ο προτζέκτορας δεν έχει πρόβλημα. Ναι, έχει πρόβλημα.
Πρέπει να κάνει την ίδια κουβέντα με τον ίδιο άνθρωπο.
Και τι, δεν μπορεί να το αλλάξει?
Δεν ξέρεις πώς είναι η διαδικασία. Κάνεις τον Έλκε και ιστορίες.
Ας τον Έλκε, άμα περιμένεις από τον Έλκε.
Κάποια πράγματα γίνονται. Κάποια. Δηλαδή στον Έλκε το... Είχαμε στη Θεσσαλονίκη αυτό που είχε έρθει ένας φοιτητής από την Κρήτη. Αυτό το ΣΥΝΕΤ που ήταν ουσιαστικά ένα σχολείο για διδακτορικούς φοιτητές.
Α, οκ. Ποιος ήρθε... Μας πεις?
Θα το κοιτάξω.
Τώρα
θυμάμαι. Οπότε είχα τώρα μόνο και μόνο να κάνω αυτά τα γραφειοκρατικά με τον Άρη. Στα νεύρα. Για να έρθουν τα χρήματα από το ΣΕΝ και από το ETS.
Και τα φέρετε μέσα από τον Έλκε?
Ναι,
έκανα πάντα.
Σωστά. Αλλά τουλάχιστον από τη στιγμή που ήρθαμε, που ήταν μέχρι να βγουν οι λογαριασμοί, οι ιστορίες, να δώσουν άλλη πάνω από εδώ από εκεί, δεν έτρεξε πολύ smooth. Και εγώ εντάξει, Simon Says, δηλαδή τι λέμε, κάτω να πιάσω δεύτερη κουβέντα γιατί γίνεται, πετάει ο Εύαρος, πετάει.
Καλά, ναι, εντάξει.
Μπορεί να πιάσει. Αλλά είναι ένα 10%. Ήταν δηλαδή, φύγανε ένα 10% έτσι.
Εννοείς το overhead. Ναι. Εδώ δεν κάνεις τίποτα και πάλι πρέπει να δώσεις. Δηλαδή, παίρνεις τα χρήματα από άλλο και πάλι πρέπει να δώσεις τον Έλκε. Χωρίς να κάνει τίποτα.
Στο Σουόνσι,
Στο Πρέμ.
Ναι, είναι Πρέμ. Έλεγε ότι 50% εκεί, overhead. Και του λέω...
Ναι, αλλά εκεί πολλές φορές τα δίνουν πίσω.
Και τι λέει η Ευρωπαϊκή Ένωση? Πώς θα το δέχεται, πρέπει να κάνει το από το Πανεπιστήμιο και το βρίσκουν κάπου ανάμεσα. Δεν πρόκειται να δεχτεί να σου στείλει η ΑΣΥ και εσύ να πάρεις το 50%.
Αλλά πολλές φορές εκεί σου δίνουν κάποια χρήματα πίσω, δίνουν σαν κάποια χρήματα. Στον Τάραμ μας δίνανε κάποια χρήματα. Όταν παίρνεις κάποιο grant, μετά κάποια χρήματα που μένουν, σου τα δίνει, σου λέει τα βάζω στο λογαριασμό σου να τα κάνεις ό,τι.
Και εγώ είχα κάποια χρήματα. Εγώ πήρα εξωτερική εγκατάσταση. Πήρα 3.000 ευρώ. Επίσης, στον Έλκη, στο Μετσόβιο, έχουν υποτροφίες για διδακτορικούς φοιτητές από τον Έλκη. Δεν έχετε εσείς κάτι αντίστοιχο?
Δεν έχουμε τίποτα, ούτε τίποτα, zero. Literally zero.
Και πού είναι αυτό?
Πάει τώρα. But it's literally zero.
Κάποια χρήματα που να έρχονται από το ΙΤΕ.
Το ΙΤΕ δεν είναι το λύση. Δεν τα έχουμε. Πρώτα απ' όλα δεν τα έχουμε καλά με τον ΙΤΕ εμείς. Με το ΙΤΕ εμείς σαν group. Δεν έχουμε κανένα connection με αυτό.
Και τώρα που είναι που πήγε στο ΙΤΕ, ο διευθυντής ποιος?
Ο Χαρμανδάρης.
Ναι, ο Χαρμανδάρης.
Ναι, ο Βασίλης. Εντάξει, οκ.
Με αυτόν δεν είναι.
Πάλι πρώτα ένα πρόλογο που θα κάνω, δεν το έχει ανεβάσει. Το έχεις ανεβάσει το πρόλογο.
Αυτό δεν πρέπει να αλλάξουμε. Πρέπει να αλλάξουμε. Οκ.
Πρώτα θα σε upgrade.
Don't praise me too much.
Καλύτερος ο δικός σου.
Εκτός αν στείλει το πρόλογο στο Βασίλη.
Είναι στο website. Θες να το ανεβάσεις λίγο το website.
Ναι, αυτό ναι.
Εντάξει.
Κάνει το λίγο ζυγό.
Δεν θα βρήκα σας. Εντάξει, άμα ήταν έτσι θα λέγαμε και μεταξύ μας. Εσείς θα το πάνω. Ναι, ότι αυτό φλος να το χωρώνετε.
Κάτσε τι κάνετε με το παιχνίδι που βάλετε στην τελικά.
Δεν είναι φλος. €5-6 και ένα χρόνο στο...
Αυτό δουλεύει το... Οκ, τέλειο. Τόταλη αντίθετα από αυτά που θα πεις.
Εντάξει, ακριβώς.
Μην το παρουσιάζεις από τώρα.
Ωραία, ωραία τα λες. Εντάξει, μια χαρά. Είναι πολύ ωραίο intro. Κολλάει πολύ μας αυτό.
Να δεις η επόμενη σελίδα.
Α, στην επόμενη σελίδα.
Και τι θα πω με τα λόγια χωρίς να είναι γραμμένα.
Να μην πεις, να μην
Θα πω,
πεις. Λίγα και καλά.
θα πω, πήγε στην Κρήτη senior research. Αλλά δεν τους έφερε αυτό. Πήγε μερικά λόγια και ξανά. Θα πω λιγάκι πιο διπλωματικά. Θα το πω. Αλλά νομίζω
Για να οριμάσεις λίγο ακόμα.
Ναι, ακριβώς.
Και πρέπει να οριμάσεις. Πάρε και μαζί όλη την οικογένεια. Δεν πειράζει, δεν έχει τίποτα άλλο και ξανά.
Δεν πειράζει, καλά ήταν. Καλά ήταν.
Ναι, αλλά δεν είχατε άλλη δουλειά να κάνετε, να φύγετε και μετά ξανά.
Καλά ήταν.
Να φωτεινά να απευθυνόταν μόνο σε σένα. Ναι. Μωρέ, καλά είναι, εντάξει. Όλες οι αλλαγές είναι πήγε σε ένα πολύ κεντρικό μέρος στην Αγγλία.
μη μου βγάλει για τη θρησκεία και μη μου βγάλει και τα λόγια.
Όχι μόνο τα παιδιά. Τα παιδιά είναι λίγο δηλαδή αλλάζοντας τη μικρή το είδα από την Θεσσαλονίκη στην Θεσσαλονίκη. Μια λίγο στην αρχή τσίνησε μέχρι να προσαρμοστεί.
Ναι, για μας το πρόβλημα δεν ήταν από Ελλάδα.
Ναι, το θυμάμαι το θυμάμαι. Το οποίο μου φαίνονταν λίγο μπράβο. Non-trivial. Δεν υπάρχει επίσης πόσο πήγα.
Για ποιο?
Ανάμεσα σε Ντάιν και Βίργκη.
Από ποιο?
Από όλα. Από αριθμητικό, από τέτοιο ότι είσαι στην Ελλάδα, ότι έχεις ταυτότητα, ότι έχεις κάτι που έχει το όνομά σου. Δεν έχεις όλα τα μπρέξ τώρα αυτά τα πράγματα και γίνονται και αυτά. Ενδιάμεσα.
Καλά φάκτορ.
Όχι, κανείς δεν κάνει πολύ.
Πρέπει να νιώθεις αυτό το χρόνο, δηλαδή αυτό το Brexit δεν παίζει να δει. Εγώ φύγαμε, δηλαδή ήρθαν πολλοί κόσμος και άνθρωποι, δεν πέραμε στους κόσμους.
Εμείς έβαλαν μια...
Πώς το λένε, ο Ιταλός πήγε στο κλίνο ψάρι.
Ναι, ο Μικέλ.
Το πήρε το ΙΑΣΥ και φύγε. Εσείς πώς μου το περιγράψατε τώρα ο Δανειστερίου. Revolving door.
Όλοι έτσι τα λένε. Όλοι έτσι τα λένε.
Ναι, εγώ το έχω ακούσει. Δηλαδή, Άστο ήταν.
Δεν πειράζει.
Ναι. Κάνει ο Ηλιάς.
Εντάξει, καλά είναι.
Κάτω.
Τώρα δεν είναι στη Γερμανία.
Στον Παγκόσμιο.
Είναι την ερευνητική άδεια που πάρει αυτό το Humboldt Awards.
Οπότε είναι τύπου σαμπάτι μετά.
Ναι.
Πώς πάει το άλλο, συμπρεβεύεται. Χθες.
Ναι, πρωτεύει.
Πάλι καμιά κοσαριά από ξέρεις.
Όχι, ήταν 30. Ήταν 30. Είχαμε και 5 ξένους.
Έχουν όμως αυτή.
Και είχαμε διαφημίσει, είχαμε πει ότι πρέπει να ξέρουν ελληνικά. Το είχαμε πει explicitly.
Ελληνικά και το άλλο.
Yeah.
Και να έχουν κάνει και τη διαδικασία του ΒΑΤΑ που πάμε τώρα στην
Το τότε δεν είναι πλέον, το κρίνει το πανεπιστήμιο.
δεν το χρειάζεται.
Δεν χρειάζεται απλώς να δεις αν είναι στη λίστα. Θα έχει απλοποιηθεί. Αλλά αυτό που έμαθα μετά είναι ότι you cannot hire non-EU citizens στην Ελλάδα, στο ελληνικό κράτος. Non-EU citizens. Δηλαδή, άμα είναι άλλος Αμερικανός, ακόμα και αν μιλάει ελληνικά ή το χαρτί, ξέρω εγώ, δεν μπορείς να.
Άκουσα στο δημόκριτο που ξέρουν πήραν. Θα το ισμάνω. Τζουζέπε που λέει Ραμποά.
Οκ, αλλά αυτός είναι Ιταλός.
Ιταλός. Έχει αγιάσει το λέω. Δεν μιλάει ελληνικά, αλλά επειδή είναι δημόκριτος,
Οκ.
είναι ερευνητικό ιστότο.
Οκ. Ναι, αυτό πρέπει να αλλάξει σε επάγγελμα.
Θα πρέπει να δίνει όμως μια τέτοια να μου άφησε σε 3 χρόνια. 3-4.
Μπράβο, ναι, αυτό είναι λογικό, ας πούμε.
Πώς
Ακριβώς, είναι λογικό.
Βάλτε στα μεταπτυχιακά.
Ακριβώς, ναι. Ναι, αυτό δεν είναι πρόβλημα.
30 άτομα. Λογικό το νούμερο είναι το ίδιο παντού. Οπότε είναι θέση του Νίκου, πρακτικά, Σάμι, αν σχετίζονται, που δεν σχετίζονται.
Δεν ξέρω αν τη μετράμε σαν του Νίκου. Ναι, δεν ξέρω. Ναι, λογικά του Νίκου είναι, ναι.
Τουλάχιστον για τρίτο αριθμό. Και ο Ηλίας δεν μπαίνει τώρα άμεσα
Θα
σύνταξη.
φύγει και ο, πώς το λένε, ο τέτοιος τώρα, ο Αθανασίου.
Όχι, άρα κάνεις τίποτα.
Όχι, εντάξει, κάνει μαθήματα, αλλά δεν κάνει γεύση.
Οπότε το φύγει μπορεί να σου θέσει.
Οπότε ναι, θα πρέπει να μας δώσει μια θέση τώρα. Τι να μας δώσει.
Ο Ηλίας είναι
Μας έφερνε
30.
στην μπούκα. Έκαμε μαλακίες. Έκαμε μαλακίες. Έτσι είναι. Μας τα έκλεισε. Αλλά δεν έκανε ένα μάθημα, ξέρω εγώ. Αλλά εμείς δεν μπορούμε. Έχει μαθηματικά μέσα, λέει, πες το τώρα.
Μα συγγνώμη. Εσείς έχετε δομές συμπληρωμένης ύλης που έχει και θεωρητικούς. Τι μπορεί να κάνουμε αυτό.
Μπορούν κάποια μαθήματα να τα κάνουν. Αλλά τα.
Δηλαδή νομίζω ότι ο Σπύρος μπορεί να κάνει οποιοδήποτε μάθημα.
Κάνει μαθηματικά τώρα. Και στατιστική.
Τα μαθηματικά, ας πούμε, στη Θεσσαλονίκη θα κάνει νομίζω προς άλλο και τα βέβαια. Κάτσε εγώ να περιγράψω τώρα να μου λένε για ποιο λόγο να υπάρχει μηχανική ανάλυση.
Ποιος το λέει.
Αυτοί δεν μπορούν να κάνουν μάθημα. Γιατί τους κόβουν τη ζωή.
Και μετά ίσως
Και είναι και το πιο, όπως το λένε, engineering πράγμα η μηχανική ανάλυση.
Άντε εκεί πέρα να το πεις ότι ουσιαστικά για τεχνολογικές εφαρμογές θες το Fourier και το Laplace. Το χρησιμοποιείς τα ηλεκτρονικά. Ποια Fourier και Laplace μπορείς να υπολογίσεις, ειδικά τον αντίστοιχο Laplace. Υπάρχει αυτή η διαδικασία, μπορείς μηχανική ανάλυση. Να είναι χέρια. Τέλος πάντων. Σου είπα το διατάφτα είναι ότι πάνε πάρα πολύ λίγοι σε θετική κατεύθυνση. Αυτή ήταν η κουβέντα που κάναμε με τον Τάσο.
Σε θετική.
Πάνε προς τεχνολογική.
Α, τεχνολογική. Ναι. Εντάξει, ναι, οπότε λογικό είναι. Το θέμα είναι αν κάποιος από αυτούς που είναι καλοί μπορεί να τους κρατήσουμε.
Και αντιβαίνει το VDA θες και κάποιους αριθμούς. Θες δηλαδή ένα συγκεκριμένο αριθμό από υποψηφίους, δηλαδή δεν θες να πέσει πολύ ο αριθμός. Αυτό που κοιτάω.
εντάξει.
Το κοιτάω είναι το εξής.
Τα λέμε να πηγαίνουμε.
Αριστοτέλειο, το 19.
Τι είναι?
Έχω κάνει μια λίστα.
Η λίστα με τι είναι?
Θα βρεις βαθμός του πρώτου, από το 19 μέχρι το 24, 161 στους 161.
Ναι.
Απλά, όταν μπήκε η ελάχιστη βάση της αγωγής, έπεσε από το 54 στους 146, με 1,2. Από τις 146 διαθέσιμες θέσεις,
Ναι.
μόνο 54 το πληρώσαν πρώτο.
ωραία.
Με τις μεταγραφές αυτό
Πώς
αυξήθηκε.
παίρνετε από γκέλ?
Από εκεί πήραμε 70.
Πήρατε 70, οκ.
Πρέπει να σου πω τι. 93 τώρα. Στους 157.
Οκ, έτσι ξέρεις πώς πέραμε.
Και το έχω. Έτσι εννοείται. Τι. Δείξτε, δεν έβαλα λαμία και καβάλα, αυτό είναι λίγο τέτοιο. Να γελάει ο κόσμος.
Πρέπει να το βάλει την καβάλα γιατί παίρνει πολλούς.
Ναι, άμα βάλει 0,8 τη βάση, ναι.
Και 0 τη βάζει, δεν έχει πρόβλημα.
26.
26. Ναι, ακριβώς.
Εδώ πέρα όμως το πράγμα είναι λίγο στη Σέμφε. Πέφτει το τέτοιο του Μετσόβιου, θα πάμε εκεί πέρα, έχουμε ένα 5 ετές πρόμο στο Βόρειο. Να ένα πράγμα που ίσως πρέπει να δώσει. Και σε εμάς θα είναι 5 ετές, με 3 ετές του προπτυχιακού. Και 2 χρόνια του προπτυχιακού να είναι μαζί. Αυτό είναι μια τέτοια. Αυτό είναι μια εικόνα που γίνεται παντού σε πολλά μέρη. Να έχουμε το 3 ετές σύμβιο. Αλλά κοίτα να δεις πώς έχει αλλάξει. Και θέλω να σου πω ότι αυτό έχει επηρεάσει τα πάντα. Κοίτα εδώ. Και την προηγούμενη χρονιά. Και σου βάζω την Αθήνα και τη Θεσσαλονίκη μόνο. Που η Αθήνα απευθύνεται σε 5 εκατομμύρια κόσμο γύρω-γύρω και η Θεσσαλονίκη απευθύνεται σε 3. Από τη Λάρισα και πάνω. Δηλαδή υπάρχει tendency. Και όταν μιλάς στο σχολείο, κάνε. Όταν μιλάς στο σχολείο, έχω και ένα άλλο αρχείο τώρα. Όταν μιλάς στο σχολείο, βλέπεις ας πούμε ποιοι θέλουν να πάνε αυτή την κατεύθυνση. Τεχνολογική. Τι είναι το θέμα? Γιατί στο μυαλό τους είμαστε καθηγητική σχολή. Έλα τώρα να τους εξηγήσεις ότι αυτό που λέμε συνέχεια σε όλα τα μαθήματα, μην απομνημονεύετε. Και εδώ σε ένα σημείο δεν θα χρειάζεται καμία εξήγηση. Θα σας έχω βάσει όλες τις εξήγησεις. Δεν υπάρχει. Υπάρχει σκέψη. Χρειάζεται μια σχέση. Θα τη γράψω εγώ στον πίνακα τη στιγμή της εξέτασης. Αυτό είναι το βασικό.
Ναι, αλλά το στα σχολεία μας δεν τις θα κάνουμε έτσι.
Όχι. Μαζί το κάναμε το λόγο. Οι Πανελλήνιες είναι 140-150 σελίδες. Σε 14 τόμους. Και οι πόλοι μας έτσι. Με ένα συγκεκριμένο τρόπο. Και είναι σαν το σκύλο του Παυλού. Βαράς την μπανάνα.
Ναι, μπράβο.
Και σου λέει. Αυτό μπορεί να είναι απίστευτα δύσκολο. Ελαττήρια, να κάνουν κολοτούμπες, να πηδάνε, να κάνουν γυμναστική κρούση. Και πάλι, και αν σου βάζει μια άσκηση και να έχει λίγο σκέψη. Άκου να δεις κορακίστηκα. Σου λέμε, ποια είναι η μέση τιμή της θερμοκρασίας μιας συνάρτησης σε μια καμπύλη. Και μου έλεγε κορακίστηκα. DS, τι DS του λέει, ήξερα τι εννοούσε DS. DS, καταλαβαίνω και το DS. Τι εννοούσε, την καμπύλη του κλίμα. Ναι, δεν ξέρω, λέω σκέψου. Μου λέει μέση τιμή, πόσο είναι η μέση τιμή. Ένα δεύτερο και το DS. Σοβαρά, και άμα η συνάρτηση είναι μονάδα του δεύτερου, θα σου δώσει μέση τιμή μονάδα. Αν του έλεγα δηλαδή DS, αν έλεγα πάνω στην τάξη, υπόδειξη, DS, να γράφω μόνο την ένα DS. Ήξερα πώς να πάνε.
Ναι, δεν ξέρουν να σκέφτονται. Μαθαίνουν να μην ρωτάνε βασικά. Αλλά είναι οι δάσκαλοι που οι καθηγητές στο σχολείο που τους τα λένε έτσι, ποτέ δεν μάθανε ήδη να ρωτάνε. Δεν ρωτάει κανένας, καμία ερώτηση. Εγώ σου λέω πάρε έναν οποιοδήποτε σε λύκειο και ρώτα τον. Ποιος είναι ο πρώτος νόμος στην Νεύτανα? Όλοι θα σου πούνε ότι είναι ο δεύτερος με μηδενική επιτάχυνση. Όλοι αυτό θα σου πούνε. Which is wrong. Τότε γιατί το βάζουμε σαν έξτρα, ας πούμε, να βάλουμε μόνο το δεύτερο να τελειώνουμε. Τίποτα, συνέχεια, consistent, δηλαδή όλοι οι καθηγητές στο σχολείο της σχολής μου, κάθε χρονιά το ίδιο πράγμα. Το ίδιο πράγμα, δηλαδή μου ήρθε να πάω και να σου πω, ξεκινήσω τεστ, ας πούμε, ερώτηση, πρώτη.
Τι θα κάνει, μαζεύεις λίγο τα πράγματα στα παιδιά.
Τίποτα, τους εξηγώ, ναι, αλλά δεν είναι. Κάθε φορά κάνω πολύ μεγάλο πρόβλημα μικρή, γιατί ήρθε ένας ο οποίος είναι τελείως άσχετος, δεν ακολουθεί καθόλου την κοινή. Τους γράφει, παιδιά ουσιαστικά είναι εκ της δημοτικού, ας πούμε, και τους γράφει. Τι να σου πω, τους είπε το εξής. Θέλει να τους πει τι είναι η μάζα. Λέει, ξέρω εγώ, λέει η μάζα, λέει, ξέρω εγώ, πόσα άτομα, ξέρω, αποτελεί το απόμακρο, πόσα άτομα έχει, ξέρω, πόσο υλικό έχει. Fine. Μετά λέει όλα τα πράγματα έχουν μάζα. Αυτό τώρα είναι γραμμένο, έτσι, στον πίνακα, ας πούμε, δεν το έχουν αντιγράψει. Τελεία. Όλα τα, πώς το λένε, όλα τα σωματίδια έχουν μάζα, τελεία. Το φωτόνιο έχει zero rest mass. Zero rest mass. Ναι, zero rest mass. Σε έκτη δημοτικού. Μετά παίρνει δημοτικού. Ναι. Και μετά, πώς το λέω, κάνει το εξής. Εκεί με εκνεύρισε βασικά. Πρέπει να τους εξηγήσει τι είναι δυνάμεις. Τους λέει τις βασικές δυνάμεις. Και μετά άρχισε να λέει κάτι κουφά του τύπου, ξέρω εγώ, η βαρύτητα δεν είναι θεμελιώδης δύναμη. Μετά τους έλεγε όχι, είναι θεμελιώδης δύναμη, δεν είναι θεμελιώδης δύναμη. Τους είχε περιτέψει τελείως. Πού να καταλάβουν τα παιδιά. Το επόμενο που τους λέει στις δυνάμεις, αν μπορείς να πεις τόσα πράγματα, τους λέει η θεωρία χορδών. Το επόμενο βήμα είναι η θεωρία χορδών. Μιλάμε για πρόσθετο στο σχολείο. Η θεωρία χορδών, αυτός είναι anti-string. Η θεωρία χορδών είναι καλή ιδέα. Ωραία. Αλλά.
Βάσκαλος αυτός.
Καθηγητής φυσικός.
Ναι, και το βάλανε εκεί.
Ναι, γιατί είναι η έκτη δημοτικού σε εμάς είναι η πρώτη γυμνασίου. Ωραία. Και λέει. Αλλά λέει, αυτή η ιδέα λέει δεν δίνει κανένα πειραματικό αποτέλεσμα. Λέει, και έγραφε κάτι είναι αποτυχημένη, ας πούμε, ξέρω. Ωραία. Οπότε το βλέπω εγώ, μου στρέφουν τα λαπάκια εκεί πέρα, πηγαίνω στη μέση και κάνω αφήνω το string theory is a good idea, is a nice idea, και πάω και διαγράφω όλα τα υπόλοιπα. Ωραία. Τότε πηγαίνει αυτός με τη μέρα, κοιτάζει τα τετράδια, κοιτάζει αυτό διαγραμμένο. Και λέει, you have to tell your dad that string theory is not a good idea and they spend so much money on it, they didn't produce nothing.
Έχει πρακτορικό αυτός. Γιατί έχει τόσο.
Τίποτα, παιδί μου, δεν έχει τίποτα. Τέλειωσε ένα master, δεν ξέρω, σε εμάς, αστροφυσική. Άσκητος. Ναι, άσκητος, τελείως. Ωραία. Τι να σου πω. Οπότε γράφω εγώ μια έκθεση στο τέτοιο, είναι στον επιθεωρητή της εκπαίδευσης. Ωραία. Ναι, ήρθα από ότι υπάρχει επιθεωρητής για όλα τα ευρωπαϊκά σχολεία και που είναι στην Αθήνα.
Αυτός είναι σπάνιο.
Και έρχεται ο τύπος στην Κρήτη και του λέω το και το πάρτε αυτό, κάνω το εκείνο, μπήκε μες στην τάξη, λέω τέτοια. Ωραία. Μου είπαν ότι θα τον απολύσουν. Ακόμα δεν τον έχουν απολύσει, αλλά δεν ξέρω τι γίνεται.
Πώς το βάζει και το τραβήξαν αυτοί.
Τι να πω τώρα.
Απίστευτος.
Και δεν είναι αυτό, εντάξει, που είναι μια βλακιά όπως ο Μπουάτας, να κάνει μάθημα, δεν ακολουθούσε καν το curriculum.
Βασίλη, το ιδέα είναι πολύ έχουν μπροστά. Ο Κλειώνης όπως και θέλει τώρα αυτή τη στιγμή στο Βασιλάκο. Αυτή τη στιγμή ο Βασιλάκος ανεβαίνει αύριο σε εμάς. Θα πάω στο αστροσκοπείο. Θα παρουσιάζει ο Κλειώνης που ήταν καθηγητής αυτό για να έχουμε τον εμφανίσει και ποτέ από ό,τι έμεινε. Δεν τον εμφανίζει. Δεν ρωτήτε. Και πάει με ιδεάδη.
Όχι, στην φυσική είναι άλλο community από εμάς. Υποστηρίζουν ένας τον άλλον, διαφημίζουν ένας τον άλλον. Είναι πολύ... Ναι, αλλά εμείς δεν είμαστε έτσι.
Είναι ιστορία του κράτους. Ναι, θέλω να σου πω ότι αυτοί μαζί με Στεριούλα είναι πάνω σήμερα. Και πώς είναι κορυφαίο. Δεν έχουμε πρακτικά ένα Ινστιτούτο Σωματολογικής Φυσικής, να σου πω, στην Ελλάδα. Είναι παρακολουθημένο. Ο Δημόκριτος είναι παρακολουθημένος. Και αυτοί παίζουν.
Ναι, και αυτοί τι έχουν ιδέα.
Και έχουν όμως το ίδιο. Αστροσκοπείο. Έχουν να κάνουν που ασχολήθηκε πολύ περισσότερο. Ο Αλβανός είναι ένας χρόνος, ήταν να κάνει το Ινστιτούτο Συνεργασίας και έχουν μονές, δηλαδή να σου γράφουν.
Η Ελλάδα είναι πρόβλημα.
Να σου γράφουν γράμμα.
Είναι πρόβλημα.
Πρόβλημα τι, τους δημιουργεί πρόβλημα.
Όχι, δεν υπάρχει το culture. Δεν μπορείς να λες πώς θα λέμε. Δεν ήμουν σε μια εκλογή. Και ήταν ένας από τους βουλευτές και λέω αυτό δεν το ψηφίζω. Γιατί είναι πολύ θεωρητικό. Λέει δεν μ' αρέσουν τα θεωρητικά. Σώπα ρε φίλε, δεν σ' αρέσει εσένα γιατί. Τι είναι αυτό το πράγμα.
Κατέβασε live κατηγορία 1. Και αφού τελειώσαν τα αποτελέσματα, δεν το πλέον.
Τώρα το τωρινό.
Το τωρινό. Ήμουνα στους υπουλαχούντες. Θέλω να δεις αυτό για την κοίτα μας. Φέρει λίγα και τα ονόματα. Τόσους τέσσερις πρώτοι, όλοι εφαρμόζονται. Πού είναι σας το αυτό.
Και μπαταρίες.
Χημεία.
Ναι, χημεία. Έκανε και εσύ photographic battery.
Είναι μία που είναι για στο είναι ένας που είναι στην Ακαδημία.
Yeah, but I would say this is a fortunate accident of building rather than the Sigma model.
Μπορεί να τελειώσει αυτό το πράγμα και με τις τελειώσεις που είναι κατηγορία που είναι θα σου πω ένα πράγμα στο 2. Θα σου πω ένα πράγμα στο 2. Είμαι εγώ και στον πρώτο 10. Μόνο αυτά. Και σου παίρνω την πρώτη βαθμολογία που είναι
99,5. Ήταν 99,99.
Εγώ δηλαδή με τέτοια βαθμολογία θα πήγαινε και θα του έλεγα είσαι υποχρεωμένη να κάνεις την εξυπόλυτη. Τι, τους υπερδαγμούς. Εγώ αυτό είπα.
And so yes, I agree. It's but there's some way that you can produce it. When you take it, you rewrite it as it's there.
But in particular with remote complex,
Yeah.
So I get my question. The twistor space is some kind of weak stroke.
So what? Why is this bad?
It's not a weak stroke.
Why is this bad? Tell me why it's bad.
I don't think so. Yeah, I mean,
Μα για να τελειώσει αυτή τη σχολή, αν δεν είναι διαφορετικά, θα σας πει πώς μετά αυτό το πράγμα γίνεται μπάκι την έρευνα.
Ναι, ακριβώς. Δηλαδή υπάρχουν διαφορετικοί τόποι. Δηλαδή το θέμα είναι καλός ο άλλος.
yeah, great question. So in the Western case, especially
Να δεις και το άλλο. Το άλλο περιμένουμε.
Τα αστέρια τι θα βγουν αυτά ποτέ. Από 2 χρόνια. Οπότε πρέπει να είχαν βγουν αναδρομικά από το
Στο Λάδο 2,8 έχει συμπράξει ερευνητικής αριστείας. Προηγούμενο θέμα που ήταν ακαδημία με ότι δεν ξανά έγινε. Μπορεί να πεις αυτά όλα στο έσος και τα σχόλια. Μάθημα την ώρα που γύρισε στην Ελλάδα. Κόπηκαν σε δίκη πολλά επεισόδια στο σχολείο. Τα μπορείς να δεις. Περιτάει μια βαθμολογία 55 η ιδέα, αυτό που έμαθα από τον Άδη και στην Αθήνα είναι ότι περιμένουν να βγουν τα οριστικά στις πρώτες συντάξεις και θα βγάλουν με τη μία αποτελέσματα. Και ήταν η ιδέα ότι δεν είναι φωλοπυρακάκια, που είναι το Golden Boy ουσιαστικά. Δεν είναι φυλασσικά στα χέρια του, οπότε άραξε πολύ λίγο. Επίσης θα πρέπει να πάμε καλά το συνδεσονιά. Μπορεί να βγει, μπορεί να πρέπει να τεχθεί μέχρι το τέλος του 25. Τόσο πάνω. Αυτό είναι καλό. Τόσο καλό.
Είναι όπως
Εντάξει, αλλά δεν είναι η χρηματοδότηση, είναι πολύ σημαντική.
εντάξει, αλλά νομίζω ότι η χρηματοδότηση από την Ελλάδα εγώ δεν θα πάρω ποτέ, ό,τι πάρω από τους. Οπότε, it's fine.
Θα δούμε και με τα αστέρια. Οπότε, χορεύοντας με τα αστέρια που ήταν στην τηλεόραση.
Χορεύοντας με τους λύκους.
Τέλος πάντων. Αυτό
Οπότε άμα είμαι περίπου εδώ νομίζω είναι fine και φωνάζω λίγο. Μα είμαι εδώ περίπου και φωνάζω.
μια χαρές. Έχεις ένα. Με το Romuald ήταν πάρα πολύ δύσκολο χωρίς μικρόφωνο.
Πρέπει να πιούμε λίγο.
So is Gabriel Doctor, they have a proposal for a well sheet or a 2D series that gives the right spectrum of attention?
Yeah, I would take. I would say. Essentially, what they let's imagine that that's the maximum.
Oh, I see. Okay.
And they work with that.
And then use representation.
Yeah,
to basically build.
exactly. That's how it works. You know how.
And then your idea would be to try and get that from a twisted space description.
Yeah, exactly. To then see if you can understand signal much more explicitly.
But it was still.
But also understanding the context of it. So one of the things that has been done.
Something there was a CFD.
Yeah, if there was, yeah, exactly. You would imagine state operating states that are described by taking these three languages certainly I already know how to do it.
So again,
Tension, yeah. This only this is very technical. I mean, one way you can so this is one thing that's slightly unclear, and I've sort of asked Rajesh about this. Rajesh's perspective would be that so one of the advantages in ADS3 is in ADS5 that's not really true unless you set G-string. And so and so you could argue that what they're doing really only applies that equals a G-string equals 0, where you would have yeah, I don't really know how to I mean, I don't know what
sorry, the twisted space. Yeah, there was some startup strike.
yeah, I know, yeah. People try. But I think there are various people that
That was very popular, yeah.
yeah, I don't think some of the reason for that is that maybe if this factorizing these because many people yeah, I mean, I don't understand the statement. So I think yes, in the Catholic source, I can't queries is whether what they're doing is really creative or just self-generated. So I think there are a lot of questions but I think certainly from what I can tell, they're giving at least a nice set of variables it's certainly providing So the hybrid system is kind of what? So what I would say the hybrid system seems to avoid a lot of illustrations of capital. So this is sort of like one of the things I've been studying. So I would argue that the way that they write down the hybrid formalism, they have the usual very sorrow constraints, and then they have some extra very funny things where they add in some extra weight 3 gauge field. The interpretation of it has been unclear. It's like a pullback of a volume 4 boundaries. But that's the extra physical state. Now, like in my work, I've really touched on that. That's how that's replaced capacity. And essentially, what it does is it renders like half of the variables so that they render the null with TSU that's got these functional generators. Half of those can use this extra so I think this is essentially how in the hybrid formalism they've kind of they've repackaged catasymmetry in a different way. And they've actually so I think it actually uses these circles that are very
No, I think precisely that. I mean, historically, the whole point of pure spin over the hybrid was to avoid like gauge. So I guess that is sort of the. But I would imagine it's actually I mean, more or less, I don't think in a height fix like a gauge in the height for example, I like little bright. Yeah, not much. The only thing I know is an appendix by Cardi Radu. It's the only paper by the so it's not really, they weren't really looking at the comments that they wrote, they weren't really looking at the manuscripts, but they were, it's basically the same, I can't remember what they find. I mean, they find something. I don't think there was anything deep about it. The problem is, I think in general the reason this doesn't really get pursued is basically a function. You know how theory in general build different S matrices. I don't know. There are these matrices that sorry, this is just like simple. So I maybe that imagine trying to come up with some but it would be interesting to see what makes sense of this. I mean, people are definitely seem to be trying to make sense of even the ONs. They can scatter correlating around the free just as that around the point of the sphere. There are various things about astronomy work. But I think this should make even more sense for a string like where there's not enough mass generation. Schroeder and start reading again. But I don't, yeah, I don't actually ever tried this seriously. Yeah, I know. I guess I don't know what to do. I think classical he doesn't really do S matrices. I mean, I think all the papers with S matrices are papers with so I think he's quite start from something here, base faces, reflecting structures, all this kind of stuff. He was trying to say that Buddha Church silence is not well defined, which is not true, and trying to define it by the figure of like cyclone manifold, say he was taking the two-dimensional space of the CP1 and just rearranging it to like a time back to three-dimensional space. And he was making it much more. No, I mean, we
Είμαστε έτοιμοι. Περιμένουμε λίγο, Κώστα, λες. Περιμένουμε λίγο. Περιμένουμε λίγο. Όχι, να περιμένουμε 3-4 λεπτά. Κρύφτορ μεγάλα, μην δείχνεις τις...
Α, δεν θες ότι...
Κάτσε να αρχίσουμε πρώτα. Άστο, αστείευα. Στο είτε έχουν αναπτύξει τίποτα σε artificial intelligence.
Ναι, υπάρχουν μερικοί που κάνουν, όπως και στη Λιμία και στη...
Σε τμήματα φυσικής όμως δεν έχω δει να γίνεται κάτι.
Στο τμήμα φυσικής εμείς όχι.
Όχι, σε κανένα.
Όχι, όχι. Κυρίως εμείς έχουμε μάθημα τέτοιο, αλλά κυρίως το χρησιμοποιούν αυτή τη στιγμή περισσότερα αστροφυσικοί, σαν τεχνική. Η θεωρητική όχι, δηλαδή ένας από τον τεσμάτερ και εγώ.
Κοιτάξτε, σε αυτά, σε παλιά πανεπιστήμια έχουμε ένα τομέα ηλεκτρονικής. Αυτός ο τομέας κάνει obsolete πράγματα. Αυτοί όλοι κάνουν κλάση, ούτε καν BC. Θα μπορούσαν, αν ήταν στο γέλος, θα ήταν στο Πολυτεχνείο, στο τμήμα του. Ένα σοβαρό τμήμα θα μπορούσε να μεταξελίξει ένα τέτοιο τομέα σε αυτό το θέμα. Πάνω το λες. Αυτά επιβάλλονται από πάνω, δεν μπορείς με δημοκρατικές διαδικασίες.
Αλλά είναι και δύσκολο να βρεις καλούς.
Γιατί έχουμε προσπαθήσει.
Εμείς προσπαθήσαμε, αλλά είναι δύσκολο.
Και θεωρητικούς, δηλαδή, αν πας πείραμα, εντάξει, θέλει χρήματα, αλλά θεωρητικούς. Δεν έχουμε προσπαθήσει, δηλαδή ανοίγουν συνέχεια σε ψέματα. Κάτσε να λέγω αυτό, έτσι. Okay. So let's go on with the public talk. So the public talk will be about artificial intelligence. This is a subject that raised in popularity the last 2-3 years, as everybody knows. It can be used, well, for various reasons. One is smart Googling. The other is big data analysis, in medicine, various other sciences, experiments in high-energy physics, banking. Could be used to manipulate people in elections or what to buy. But what about theoretical physics? In our subject, we are driven by curiosity. We don't care immediately what we find to find applications. So the question is, does artificial intelligence has a place in theoretical physics? And the question here is it just to do things faster, or can help people, scientists, to make easier, let's say, conceptual advances? That's the question. So the person to tackle this problem in this workshop, how do I proceed with the transparency?
Wait, you can.
Okay. So that's the last one, don't worry. So the person to talk about the subject is Vasilios Niarchos. So let me tell you a few things about his career path. He finished our university, the University of Athens, in 1998. Then, as it was at the time the habit, the best students go and do a PhD in the US. So Vasilios went to the University of Chicago, where he got his PhD in 2004. Then he did a series of postdocs in very good places like Niels Bohr Institute in Denmark, École Polytechnique in Paris, then where he had some Marie Curie fellowship, and then for quite a few years in the University of Crete as a senior researcher. That was not enough to get him a permanent job there, so he went for a few years to the University of Durham, and then he returned back in the University of Crete in 2019 as an associate professor. Very recently was promoted to professor, and his research topics, as you might have already an idea from his talk, and his from Inspires and elsewhere, is on string theory, QFT, and gravity, and in particular intersection between these three topics. And the reason he's giving this talk today is because in the last few years he implements methods of artificial intelligence in tackling problems in non-perturbative quantum field theory. Okay, so Vasily, the floor is yours.
Thank you very much. Thank you very much, Costa. So let me change the slides. Oops, what happened? Okay, very good. Thank you for the introduction. It's a pleasure to give this general public talk, especially because it's in my alma mater. So I want to, Kostas set it up very nicely. So basically, I will not go into a lot of technical details. I will mainly try to discuss general concepts around AI and possibly whether some of the techniques that are being developed there are useful for us. So it's basically mostly an exhibition of examples and concepts through examples from our field. And you will be the judge whether this is something useful for you. Okay, so let me start from Wall Street, not from AI or physics. You all have heard about DeepSeek. A few months ago, this paper here on the right appeared on the archive at the end of January this year. And this is what happened when the markets opened the next day. Basically, all the tech stocks in Wall Street sharply dropped, especially NVIDIA, which makes all these fancy GPUs, chips that people use to train AI models. And as you can see from, this is basically a photocopy from the Wall Street Journal website. You see DeepSeek undercuts belief that chip-hungry US players will win AI race. But what's really amazing to me is like a paper from the archive really has this huge immediate impact. Now, we'll come back later on this DeepSeek paper to discuss, some of its aspects, but I want you to sort of pay attention a little bit to the following aspects here. First of all, I won't read the abstract, but some things to keep in mind is that basically what these guys are trying to do is try to find a cheaper way to train these large language models. And in particular, what they're trying to achieve is higher reasoning capabilities for their models. And what really scared the market is the fact that they were able to do it in a much cheaper way than, for example, OpenAI that has ChatGPT. Another thing that, another term that appears here is reinforcement learning that we will encounter later on. Also, another thing that I want you to pay attention to is like, for example, well, two things. One thing is that unlike OpenAI, they open sourced their code, so everybody can play with it. They can download it on their computer, which is a major difference. Another thing is that here they say that they give you some relatively small models, distilled models, and the number of parameters is of the order of a few billion. If you ask ChatGPT how many parameters ChatGPT 4 has, it will say about 1.7 trillion parameters, okay? And you can see it's really competitive on reasoning tasks. Okay, so let me drop this. So obviously there is a lot of impact of AI on commercial applications, but already the previous slide hints on the fact that people are also interested, for various reasons, on reasoning capability, right? And this is very important for us as scientists because a useful tool for us will be a tool that can actually think. And here is an abstract from another paper that appeared in August last year. I will read the abstract here. Basically, I like the abstract because it has all the words I would like to say. And it gives a sense of what people are thinking about. Like it says, one of the grand challenges of artificial general intelligence, AGI, is developing agents capable of conducting scientific research and discovering new knowledge. While frontier models are the foundation models like ChatGPT, have already been used as aids to human scientists, for example, for brainstorming ideas, writing code, or prediction tasks, they still conduct only a small part of the scientific process. This paper presents the first comprehensive framework for fully automatic scientific discovery, enabling frontier large language models to perform research independently and communicate their findings. We introduced the AI scientist, which generates novel research ideas, writes code, executes experiments, visualizes the results, describes its findings by writing a full scientific paper, and then runs a simulated review process for evaluation. Okay? Now, I read the paper. It's an interesting idea, but it gives you a sense of what people are trying to achieve. It is indeed somewhat effective in, say, computer science, not the most complicated task, obviously, or the most complicated paper in computer science, but I find it very hard to believe how it will be able to do this kind of process in our field. Okay? It looks impossible. Okay, so before I go on, I would like to make a distinction between two kinds of things. Like when one sort of thinks about the topic and says, okay, I have this set of methods, new methods, what would I like to achieve? Well, one, the more traditional approach that you can take is that, well, look, we have been using machines forever in science, right? Like since the abacus, when we were counting numbers in the ancient times. So this is not new. Now we have a new set of tools, and they perform all sorts of different tasks, and we can use them to supplement what we're already doing with computers, like computational tasks. For example, it could supplement things that we're already doing with Mathematica. Okay, so you can view AI or ML methods as a new toolbox for novel computational techniques, and basically today's focus will be this one. So I will go through basic techniques or categories of machine learning methods, and I will give you examples in some examples, by far not a complete list of what has been done in our field, but some examples that tell you what kind of things you can do. Okay. But the more radical approach is one where, and it is hinted by the previous slides, is one where AI and human intellect basically share the driver's seat. So in the first approach, where we command the game. Basically, we set the problem, we're thinking about the problem, we generate the ideas, and then we end up, I don't know, with some set of equations that we want to solve, and it's a practical problem. But here, it's much more impressive. So what if you had algorithms that are great at reasoning, that they can brainstorm and give you new ideas, you can collaborate with them, and maybe even solve some problem. And usually here people have in mind large language models, like ChatGPT, for example. It is quite likely that real breakthroughs in science are going to come from this direction, but this is still much under development. Good. So in this talk, again, I don't want to approach the subject from the point of view of computer science. Really, what I'm interested in is how I can use all these new methods to say something new or make some progress in problems that I care about in theoretical physics. Now, we can ask more generally, can AI be useful in physics in general? The answer is immediately obvious, yes. There are many areas of experimental or observational physics, and more generally physical sciences, that are using AI methods or machine learning methods very actively already for many years now. Experimental high energy is, of course, a great example. People from chemistry, materials, biology, medicine, basically wherever you have to deal with big data and you have to find patterns, whatever, AI has been a great tool. But can AI be useful in theoretical physics? It's not so obvious. In fact, like none of our talks, for example, used any of these methods, right? And most of the tools we're using are not really very good for the kinds of problems that we want to solve. So the number of AI applications in this area is less widespread. That's obvious if you compare with other areas. So what I want to do is go through some examples from quantum mechanics, quantum field theory, and mathematics to see if there are some potential gains that we can make by incorporating some of these tools in our toolbox. Now, before I do that, I want to ask, in some sense, I want to ask, is theoretical physics hard for AI? I mean, why has it been so hard for us to apply these methods? And I will, again, use a phrase from the DeepSeek paper that says, this phase focuses on enhancing the model's reasoning capabilities, particularly in reasoning-intensive tasks, such as coding, mathematics, science, and logic reasoning. All of this stuff are stuff that are of interest for us, which involve well-defined problems with clear solutions. So basically, I really need to bring the problem at a stage, essentially at the final stage, and then these methods will solve it, okay? So many of the most interesting problems in what we do are faced with both conceptual and computational problems. It's not just conceptual. And in other areas, they have a very clear computational problem that they have to solve. There are lots of data, so this is all data-driven. And then it's easy to use these methods. Moreover, many of our problems, and I think it's evident from many of the talks we heard so far, involve structures that go beyond, first of all, they involve structures that are typically not finite dimensional, they're infinite dimensional, so it's typically hard to put them on a computer, okay? And also, traditionally, in our field, sometimes we have to go beyond the mathematical structures that are already available. Like in theoretical physics, generated new mathematics along the way, okay? So there is also another difficulty in applying these methods. Theoretical physics, as I already said, is typically not data-driven. Okay? It's not like astrophysics or whatever, or chemistry or material science. We play a lot with concepts, and we do not have this aspect. And moreover, a lot of what we do requires rigor and interpretability, but ML methods are usually stochastic, error-prone, and black box. So even if they give some result, we want to be able to trust the result, and that is not obvious. Okay? So the question here is, how does one extract reliable analytic information from typically statistical methods? That's one of the reasons, basically, why typically we don't use such methods. We're not accustomed to using such methods. So I want to give an example. The example is extreme, okay? But I want to highlight it as an example where really it's nothing, because there's nothing conventional about this example, okay? So, you know, two of the big problems in our field, well, the problems that drive really our field, is how to make sense of quantum gravity, how to put together, we have two excellent frameworks, classical gravity and quantum mechanics. We want to put them together as a framework of quantum gravity. And this has been driving a lot of our efforts, okay? Another very difficult problem is, well, we know how to do quantum field theory to some degree, but not really quantum field theory non-perturbatively. Again, a lot of talks encountered this problem. And string theory, which is an even more complicated encompassing framework, came out of this effort to solve these problems. So it provides a more general framework where some of these answers can be understood, and this framework itself is very poorly understood because it's very, very complicated. In particular, as an example, string theory predicts an exotic QFT in 5+1 dimensions that everybody here knows. It is called the 6D2,0 theory. It has no tunable coupling. It is inherently strongly interacting. And more importantly, it's one of these examples that doesn't have any Lagrangian description, right? The first thing we learn about in first years in university is you give me a Lagrangian or a Hamiltonian, and I know what to do after that. This is the basis of mechanics, is everything. Okay, but this one doesn't seem to fit in this framework. I like to mention these examples in front of my condensed matter colleagues who have a shock. They cannot think that it's possible to do anything without a Hamiltonian. So standard non-perturbative QFT methods, like non-perturbative means beyond perturbation theory, we don't have a lot. One of them is lattice field theory, and we will not have been able to apply this here because there is no Lagrangian, okay? So again, what am I trying to say here? I'm trying to say that we, in our efforts to understand better the frameworks that have already been proven as very valuable frameworks in physics, through a long sequence of logical arguments were led to a more complicated structure, and we're really lost how to navigate through the structure. Okay, and it's really a conceptual problem. It's not simply a computational problem. So it doesn't fit nicely into this, basically these kinds of problems that involve well-defined problems with clear solutions. Okay, good. So having said this, okay, let me now try to propose 3 ways in which we could try to use existing ML methods or artificial intelligence methods to advance some of the problems that we're thinking about. Well, the first one is to try to use these methods to efficiently manipulate and learn infinite dimensional structures. For example, all sorts of kinds of functions, okay, that appear in our problems with deep learning methods. And here a keyword is representation learning. Representation learning is crucial, is a big deal in computer science. How you extract, important information from a complicated structure, for example. Another thing that we might want to do is to learn how to transfer knowledge from accessible corners of the theory to inaccessible corners. And, as I will mention later on, there are many situations where, we have a quantum field theory or whatever, some quantum system or some other physical system. We understand part of the story in some easily accessible corner, but then it's very hard to really understand the full story. Can we transfer knowledge from what we understand to the more complicated general picture? Another thing we can do is try to discover new solution strategies. We're solving problems, so maybe we can find some new ways of solving them. And again, the point I'm trying to emphasize here is what I'm trying to propose is not that AI is some magic box that's going to come and magically solve all the problems that we have. Clearly not. But I think that there's going to be a lot of fun and potentially a lot of gain if we use them alongside methods we have already developed, or an analytical understanding we have already developed to take the next step. And that's precisely what I'm trying to emphasize here, that all of these directions, if we can implement them in any successful way, they will require the clever incorporation of domain knowledge, okay? Stuff that we're already doing, okay? So what's the plan of the talk? The plan of the talk is really simple. I want to take these 3 points and illustrate relevant techniques and set up some language from deep learning, basically, for those that are not familiar with it, through examples and applications in theoretical physics, basically quantum field theory, and one example from mathematics. Okay, so let me set up some language first. When I talk, first of all, machine learning means a set of a lot of methods. Some of them involve neural networks, other methods do not involve neural networks. Usually when we talk about AI, we have in mind things that involve neural networks. So neural networks are going to be important for us. And so the point is that neural networks are a particular way to model functions, okay? So usually you will see this picture. There is input 1, 2, 3, 4, 5, n, whatever, and then there is a number of outputs, and you see all these neurons. They're connected like this, and they remind a little bit the human brain or whatever. But the concept is really, really simple, right? It's basically how do you represent a function. Now, we know many ways of how to represent the function. I don't know, you do some Fourier analysis or whatever. This is another way to do it. And it's really elementary. What you do is suppose that X is the space, your domain, the vector from the domain of the function. So this is the input. You take it, you act with an affine transformation. So basically you do linear transformations and you add a shift. Then you pass it element-wise through a nonlinear function that usually it's some simple nonlinear function, like tan h, for example. And then you repeat this many times. So every layer here is essentially one of these steps. So it's a composition of affine transformations composed with a nonlinear function. Very simple, okay? And there are universal approximation theorems that tell you that if you take the width to be sufficiently large, then you can approximate any function with some assumptions, general assumptions, within some error. Notice that by doing this representation, I managed to represent the function in terms of a number of parameters. The parameters are basically these WMNs, which are constants, and these BNs. I will collectively call them as a vector. I will denote them with the vector theta. Okay. So when I was saying that, for example, in the abstract of DeepSeek, that there is a model that has 70 billion parameters, I'm referring to these types of parameters. Okay. Now, there are some other keywords here. For example, what does it mean to train a neural network? Again, the concept is very simple. You want the function to have some properties. For example, you want it to have specific values, or you want it to satisfy some equation. Okay? The idea is to tune your parameters theta so that your function fits the criteria that you want it to satisfy. And typically, this involves solving a complicated non-convex optimization problem. And this is typically hard and rather costly. So if you have a model with 1 trillion parameters, obviously you're optimizing in some 1 trillion parameter space with some landscape that is very complicated. That can be a really costly operation. But that's all we mean. So basically, training means fitting. Find the parameters that reproduce the function that you like. There is also another thing called hyperparameters. When you do the training, you can do the training in all sorts of different ways. I don't know, like use different optimization algorithms, use different learning rates. You know, there are all sorts of parameters that are not optimized during this process. Okay. But you're free to choose them in some particular way. And sometimes you choose them in some way and optimization works great. Other times you choose it in another way, the optimization doesn't work at all. So scanning over hyperparameters to find the optimal hyperparameters is not an easy task. It is also a costly business. Another word is architecture. What I showed you here is the simplest feed-forward neural network architecture. So everything is fully connected, just go forward. But you can imagine other kinds of architectures, and different architectures could be better for different problems. So there are different kinds of algorithms of type of neural networks that are good for achieving different things. For example, for, I don't know, like for pictures, you want something which is known as a convolutional neural network, okay? Or for sequences, you have other kinds of neural networks. A popular architecture for language, for large language models, in fact, the main algorithm that is in ChatGPT, in models like ChatGPT, is something called transformer. Here's a quick picture of how the transformer looks like. It still contains stuff like this, but it also has other built-in features. Now, there's another thing that you can also do. So far I was emphasizing the fact that we can use neural networks to model functions, okay? But another thing that you can do, which I think is really cool, is you can also model operators, so maps between infinite dimensional spaces of functions. For example, suppose that you need to solve an initial value problem and you give some initial condition with some specific function, you solve your differential equation, at later time you have another function, the time evolved function. Instead of solving the function, it would be nice to know the map that takes you from the original, the initial value function to the final function automatically. Like in quantum mechanics is the time evolution operator that does that, okay? So it is possible to learn operators using neural networks, okay? And this is one way, for example, to solve complicated differential equations, like, for example, Navier-Stokes equations, okay? And I will give some examples later on of this. So during training for a neural network, what you do is you have, I don't know, 1,000 samples of X, you pass them, okay, and you say these are 1,000 outputs, and you try to fit things with a ground truth, for example. Here, instead of passing points, I pass whole functions. I pass function 1, function 2, function 3, etc., and I get, I don't know, 1,000 different functions as output. And try to learn the weights and biases, all these parameters of a more complicated architecture that will fit basically this map, okay, between the functions that are input and the functions that are coming out. So this is called the neural operator. So now let me go through these 3 points and try to illustrate examples, applications of these algorithms. So the first one, remember again, the first one was efficiently manipulate and learn infinite dimensional structures. As an example, here I will focus on learning functions by solving equations. Pretty standard thing. And this will also give us example of what is called unsupervised learning. So the idea is that we can use neural networks to find an alternative to standard numerical methods for systems of equations. And these equations can be very general. They can be systems of algebraic equations. They can be systems of PDEs, integral equations, whatever. Okay? So the idea, the name of the approach here is called PIN. It's called physics-informed neural networks, because basically you try to fit a function that satisfies an equation. For a computer scientist, an equation that comes from physics already tells you that this is a physics-informed neural network. Okay, although you could use it for other purposes. So what's the idea here? Pretty simple. You want to solve for a function. Neural networks give you a way to approximate functions. So you say, I will model the function as a neural network. And then I will try to put the equation as a loss function. Tells me basically what is the error. So, you know, I have some weights. I produce some function. I plug it into my equation. I see how bad is it. Okay? Then I try to manipulate all these weights so that I bring the loss function down, and hopefully achieving to great accuracy essentially loss close to 0. Okay, then I have satisfied, I have found a neuromorphic approximation of the function that satisfies the equation that I want to find. And this is what training means. It means find all these weights and biases, all these parameters that give you a neural network that minimizes the loss. Obviously, it's an optimization problem. Okay? And if your neural network has, I don't know, like 3 million parameters, then you have to optimize in a 3 million dimensional space. Okay? Now, the nice thing and the thing that has actually given a lot of impetus in the last few years is that people realize that stochastic methods like stochastic gradient descent can efficiently solve such problems. So you put it on a computer and stochastic gradient descent, for example, which is a typical optimization method that people use, works pretty well. So instead of giving you an example here from some standard PDE, let's say Navier-Stokes equation, let me give you an example motivated by quantum mechanics. I mentioned this example also in our first COST meeting, but I want to repeat it. You'll see why it's a nice exhibition result. It has some features that, I don't know, solutions, for example, of PDEs do not have. Okay. So what's the problem here? So here, this is an aside on quantum mechanics. So suppose that I do, again, I go back to standard quantum mechanics from an undergraduate course, and I do scattering in 1 or 3 dimensions. 3 dimensions, for example, is more interesting, where I have a target modeled by some potential, and then I send in some incoming wave, it scatters, and then it gives them, with some probability, I observe a beam in this direction, that direction, etc. So one way to solve this problem is to solve Schrödinger's equation, time-independent Schrödinger's equations, and find the eigenstates of the energy that represent the scattering process. And the large distance asymptotic form of the wave function is what we call the scattering amplitude. Okay, it's part of the wave function, so you square it, you find probability. That probability basically tells you what is the probability to see the particle here, there, there, okay? Which is more carefully phrased as a differential cross-section. So this is a basic relation in quantum mechanics scattering. Differential cross-section is equal to the scattering amplitude squared. Now, the scattering amplitude, as I said, is part of the wave function, so it's a complex function. It has a modulus and a phase. But when I do the experiment and I collect data from different angles, right, I get information only from the modulus, not from the phase. So I cannot directly reconstruct the whole wave function. Now, why would I like to know the whole wave function? For example, if I go at very high energies and work to leading order in a perturbative expansion, if I know the full wave function, I can Fourier transform it and get information about the potential that does the scattering. Okay? So you want to ask if you can reconstruct the phase of the scattering amplitude from information that you get from the scattering experiment on the modulus B of z. And there are several ways to try to attack this problem. First of all, you know, when I solve Schrödinger's equation in 3 dimensions, one way to do it is do an expansion in spherical harmonics, right? And since I assume here azimuthal symmetry, it's basically an expansion in Legendre polynomials. Z for me is cosine theta. Theta is one of the spherical coordinate angles. And this is a formula that you know very well. Basically, I can express the scattering amplitude as an expansion in these polynomials with some coefficient, and there are some real parameters that appear there that we call phase shifts. So if this is a finite sum, then a finite number of such parameters completely characterizes both the modulus and the phase, the full wave function, the full scattering amplitude. Okay? So as a human, for example, this is easy for me to understand, right? You have 10, 11, whatever, 1,000 parameters. It's a finite number. I know the function. Okay? It's easy to play with this. But typically, the scattering amplitude is not going to be a finite sum. It's going to be a sum involving a whole series. So now I have to deal with an infinite dimensional, something that has an infinite number of parameters. So people asked this question in the 60s and 70s, and it was studied by various well-known people like Martin, Atkinson, and others. And the key to understand the relation between modulus and phase is unitarity. basically the fact that total probability is always 1 in quantum mechanics. So then, there is an argument that you can make, which you can find in Landau-Lifshitz, tells you that the phase phi and the modulus b, here I multiplied with the momentum, the actual phase, so I call this capital B. So these two functions, I have two functions now of basically z, which is cosine theta, and they are related by this integral equation. Okay? So all my ingenuity led me to this equation. Now I have to solve this equation. So the game here is you give me B, because I read it from the experiment, and then I tell you, I solve this equation, I tell you what phi is. Okay? And I reconstruct the wave function. Notice that this equation, okay, it's not the most complicated equation you have ever seen, but it's also not the simplest one. For example, here you see I integrate over z1 and phi 1. Z2 depends both on z, which is the external parameter, z1 and phi 1 in this particular way here. Okay? So now you can ask, can I give you any b and you will get a phi? And the answer is no. For example, if we said z equals 1, which is an external parameter, here you see if I said z equals 1, this goes away. This becomes 1, so z2 equals z1. But when z2 is equal to z1, this is cosine of 0, so it's 1. And therefore, I get just an integral of the input function, b. So this thing is going to be sine of some angle. And it better be less or equal than 1. So if you give me an input function b, whose integral, this integral, is greater than 1, I won't be able to solve that equation. Okay? So this is an example where, like there are, sometimes you get a solution, sometimes you don't get a solution. Okay? So it makes the problem, later the problem of solving it, or the, if you want, the ML way of solving it more interesting. Secondly, there are additional bounds on existence and uniqueness that can be obtained by defining this function, where basically it's the same integral, but I just dropped the cosine. And then I can look at this k of z, look at all the values that I get I scan over all the values for all possible values of z, and I get the largest number, and I call that largest number Martin parameter. Okay? Now, formally, it is denoted here as sine of mu. It is denoted like this because you can argue when this number is less or equal than 1, just like a true sine, okay, then you can argue that you can always construct a unique solution. Okay? But if it's greater than 1, solutions may or may not exist. They can, if they exist, they can be unique or doubly ambiguous. Okay? And to this day, people don't really know what is the general story. Okay? When ambiguous solutions appear or whatever. So recently, Darcy, Schwartz, and Zhiboedov wrote a paper where they used a pin.
This mu is could be complex.
Yeah, exactly. Or yeah, sine mu is not a good name for it. Okay, so think of sine mu as a formal way of characterizing this parameter. Okay, I didn't even have to use sine there. Okay, so so these people used a pin to solve the above unitarity equation with remarkable results, including the discovery of a new ambiguous solution with the lowest known Martin parameter, around 1.67, which was essentially the world record, the new world record after 50 years. Because people were looking what is, the ambiguous solutions with the lowest possible sine mu. And there were some results, so this was basically the new world record. Okay? So how did they do this? Again, the idea is very simple. You're looking for a function, okay? Model it by a neural network, characterized by some parameters theta, and then formulate a loss function, which is basically your error. So you compute, say, this equation is the left-hand side minus the right-hand side. You evaluate it at a number of points. So you discretized your z values. So say you take 100 values. You evaluate essentially your error in 100 points. You square this, you sum and average. And basically, you're trying to tune all these parameters theta so that this becomes very small. That's the game. Okay, so that it's very simple. And then you minimize with respect to these parameters, theta. And these are some plots of what they got. For example, if they scan, again, you have the possibility of scanning all sorts of different functions, right? So, but they scanned here as an exhibition on linear functions, B, and quadratic ones that you can easily argue do not have a finite partial wave expansion. And red is basically no-go regions. They are not finding solutions there that have low error, okay? This gray curve is the curve that is set by the exclusion bound, this one. So everything outside it should be red. It should not be possible to find a solution there. Indeed, the pin doesn't find any solutions there. Inside, it's not clear, okay? But you know that you should find solutions inside this I, which is bounded by sin mu equals 1. So sin mu less than 1, we know from theory that there should be solutions. Indeed, they find solutions there, okay? It's more complicated when it's quadratic, okay? There they find these solutions are spurious. They just numerically close to some finite partial wave solutions, but they shouldn't really be there. These two ones, these two little islands here, are solutions that should be there. They're in fact L equals 2 solutions. Okay, so this is an example of unsupervised learning. Why? So why do we call it unsupervised? Because in this particular case, we do not need to prepare beforehand a set of data, experimental data, if you want, that will guide the search. Okay, so the algorithm generates its own data and does and optimizes. Yes.
In the previous transparency, what is at the end admissible is the common area, the common blue area.
The blue area. The blue area is the admissible one.
If I keep going with different polynomials, should I string it more and more?
It changes. It's still an I, but depends on, you know, I mean, I've gone up to cubic order, for example. It's very similar. Okay.
So you're going to ask something?
Yes.
I'm trying to understand what exactly was done here. It's an optimization problem.
Yes, that's right.
But why don't you optimize your original function, you know, just parameter it any way you want and optimize that?
You can do that. The point is to find an expressive enough parameterization that will allow you to approximate the function you want to approximate. But up to this point, that's why I'm trying to say it's very, very general. Yeah, exactly. Exactly. The new element is that I have now a generic way and a generic expressive way to represent functions through a neural network representation. That's it, right? You see, it's very simple, and I'm trying to present it as very, very, very simple.
Just as a mini think or whatever, just optimize something.
Exactly. Well, the optimization may not be practically easy, right, and wouldn't have been possible a few years back. It's possible now in modern computers, right? But the idea is very old. Right? Even with this representation is old. It goes back to the 90s. It's just that they didn't have the computers to put it on a computer. Okay, that's it. So it's very simple conceptually. Good. So you might have heard of other applications in our field of basically the same method. Like all these applications with numerical Calabi-Yau metrics are morally in the same class. Okay, as they're solving the Einstein equations. Okay, they are looking for Calabi-Yau metrics. Of course, they're using a lot of domain knowledge to, you know, they don't take the raw Calabi-Yau, the raw Einstein equations. They make all sorts of ansatz. They use, I don't know, like supersymmetry, whatever, write things appropriately. A lot of domain knowledge goes into this, and then they parameterize things with neural networks. Okay, but again, morally speaking, it's not something complicated. Okay. But the thing I want you to appreciate, and maybe will be useful for you practically, is, you know, it is a way to manipulate functions. Okay. So now let me up the game a little bit and ask the following question. What happens when the model is unknown? Like we don't know this equation, for example, right? Or we don't know, I don't know, like the Lagrangian or whatever. And there are only a few experimental data available about the structure we want to uncover. Then what do we do in that case? So usually this involves information restricted in some corner of parameter space. So we could think of ourselves as experimentalists of the mathematical world, and we can ask, can we identify new structures and learn the model from the available observations? Can we transfer what we learned from a restricted corner to the inaccessible, the hardly accessible regimes, generating new predictions and or conjectures? So this is point 2 of part 2 of the talk. Okay, so how do I take information, restricted information from a corner, and sort of like generalize it somewhere else where I cannot do any calculation with traditional methods? That is much more interesting. Okay, and to bring it into context, so suppose that you performed a nice complicated computation in a weakly interacting quantum theory, quantum field theory, for example. Can we learn something about the non-perturbative properties for the theory? It's not clear that we can do it, but in some cases it might be possible to do it. You know, sometimes, I don't know, like for example, we discover some structure like topological and topological relations or whatever in some supersymmetric theory, and we find that the data we want to compute satisfy they have some hidden structure. Maybe these methods can discover the structure and then can generalize it into a non-perturbative regime. That's what I have in mind. Or we did an exact analytic computation using special properties. We used symmetry or supersymmetry, for example, or integrability. We had a lot of nice talks about integrability in this workshop that allowed us to compute a set of semi-protected data. Can we use this information to learn something about the generic unprotected observable? That's really what motivates me in this subject. So let me go to point 2 and keep going with the same example. Okay? So now what I want to do is take the same example, but I want to remove basically the human input. I want to remove the fact that we know this integral equation that relates the modulus with the phase. Okay? So what do I want to use? I want to use only the fact that if I have a finite partial wave expansion, I can easily generate consistent scattering amplitudes. Because it's a finite sum, I plug in whatever phase shift that I like, and I get a function. Okay? And that gives me examples of consistent functions, consistent scattering amplitudes, but nowhere in there have I input a complicated relation like this one. The question is whether I can discover it just from this very limited data in the easy corner, which is finite partial wave expansion. So can we learn the map, the operator between the infinite dimensional spaces of modulus functions b of z and phases phi of z, or when a phase does not exist, just from the data of finite partial wave expansions? That's what I want to ask. And this is what we tried to do with Kostis Papageorgakis in a recent paper. So we trained a neural operator on 300,000 true b phi samples, just basically generate randomly phase shifts and rid of b phis on a cluster with one of the NVIDIA chips. And then we produce an operator that once you give it a B, you do it only once, by the way, the training. Previously, in the pin case, you gave me B, I have to do an optimization problem, I tell you what phi is. You give me another B, I have to redo everything from scratch. Okay? Here, I do the training only once. I give it 3,000 different functions, and it learns how to make predictions on generic B. Okay? And so we have now this neural operator. It's trained on finite partial wave expansions, and we ask it to make predictions on infinite partial wave expansions. Okay? How well does it do? Well, here I have to stop, right? I cannot do anything, really. I mean, I have the prediction, but really I cannot do anything with it. Why? Because I don't have any way to test the prediction. Right? I removed that equation, the unitarity equation. So I can make a prediction, but how do I test it? It could be garbage. I don't know, right? It will make predictions even when there's not supposed to be a solution. Okay? And that is a generic difficulty in this game. It's not enough to train, right? Reliability, being able to say with certainty that what I found is correct, is super important. Okay? Now, for a moment, give me the ability to bring back that equation, okay, and make a similar plot like the Darcy et al. Plot. You see, it makes pretty good predictions. So it was trained, okay, so for these linear profiles, the losses are down, a bit higher than the pin results, but it can actually generalize, okay? So it's now making predictions that are basically correct
in a case that it hasn't seen before, which means it has learned that equation, that complicated equation, simply from finite partial wave expansions, okay? Good, but let's go back, okay? Let's.
What is this curve between, which connects the eye to the...
This one?
Yeah,
this is like, there it's not super accurate. It seems to be seeing something here, okay?
So before you knew that anything outside should not be there,
yes,
this is consistent with the red color.
Right,
now
right. Now it's not super accurate, right? It's ballpark correct, okay? But obviously I'm not doing the super intensive like work that I was doing before, because now I'm generalizing on a case where it hasn't seen before. I think what we need to take from this is that with these assumptions, it didn't do such a bad job. Okay? Yes?
Could we do an intermediate step and give the information about the concept of unitarity without the unitarity equation?
I have given it, indirectly, I have given the information about unitarity by using the fact that the phase shifts are real. Okay? This is where the information is. Okay? But it has to recognize that and then generalize in a situation where there are an infinite number of phase shifts. That's a non-trivial thing.
So the information about unitarity is there?
It's there, right. It's there, but it has to recover it in a more general context. Yeah. So, so this is a generic difficulty. So what did we do next with Kostis? We said, okay, we need to understand this. Okay, so let's do the following thing. I mean, we have been showing it through examples. We have been telling it what is a correct B-phi pair, okay? But we haven't told the machine what it means to make a bad prediction. So it just makes predictions and things, all are on equal footing, okay? So to address this problem, we retrained the neural operator, exposing it to 225,000 true pairs, just like before, and 175,000 false pairs. Right? So here we generate, basically we take, the B's and the Phi's are completely random. Okay? And at the same time, we supply the neural network with an extra label, a classifying label, that tells it, this pair is correct, this pair is wrong. This pair is correct, this pair is wrong. Okay? So in that sense, we run a simultaneous classifying regression task. Okay, regression is find the function, classification is it correct, is it not correct? Okay?
Sorry, but binary or almost correct? So it's correct?
No, here during training is 0 or 1. Okay? Obviously, when it makes predictions now, it will spit out a label, and that label is going to be some number. It doesn't even have to be between 0 and 1. This is how we set it up. So it could be some number. Okay? Now, we would hope that B very close to this parameter F close to 1 means that it thinks that it's a correct solution. I should trust it. So now I have a new function defined in terms of weights that I would have never imagined defining on my own by trying to understand the problem, okay, that potentially has something to do with the unitarity equation. Okay? So, and again, I find this quite out of the box, okay? So here I'm plotting again on the right-hand side what I had before from the more accurate Dersi et al. Plots. On the left, basically I'm plotting this F. So now the colors are inverted. So red means it's allowed, blue is disallowed, okay? Now what I take out from this is that very sharply distinguishes allowed and not disallowed and makes islands of allowed regions. Again, just like with the bootstrap, it gives me a disallowed region. And the disallowed region is basically always correct. Okay? So not only that, what really surprised us is that, look, before here.
And how do you know that it converges to a certain state at the end?
Well, again, all of this is, rarely there is some analytical understanding behind this. As always, computer science people, they do the experiment. So we do the experiment, this is what we observe, and that's what I report. Okay? Indeed, I would like to know more than that. But notice here, when I did this plot, these two blobs of allowed solutions were not there. I couldn't see them, right? When I do it, when it uses its own criterion to say, is there a solution here or not, it finds these two islands, and they are precisely where Dersey and all found it. So merely the fact that it was trained also knowing bad solutions, it has a better understanding of the equation. Okay? Yes. So let me give another example. Again, this was a quantum mechanics example, again, a scattering amplitude example. As you know very well, in quantum field theory, we're interested in, this is where we do scattering experiments for QCD or whatever, and we can really solve the theory at weak coupling, so we organize things in a perturbative expansion. Higher orders means more loops, more computational complexity, so although this is an analytical method, it's not exact. You do one loop, you do two loops, after a number of loops, you're dead, okay? So people have been thinking hard in this business how to make more efficient calculations, like don't compute directly the integrals, okay? Try to understand what the answer is, and try to bootstrap the answer, okay? So in recent years, much progress has been achieved in high loop computations in planar n equals 4 Sperry-Yang-Mills theory, and the idea is bootstrap the answer by studying the space of functions where the amplitude lives and the relations it must obey. I find this an extremely nice idea, this whole bootstrap idea, and how it could be married with this kinds of methods is also one of the driving forces in what I want to do eventually. So many amplitudes can be expressed in this game as linear combinations of generalized polylogarithms, basically integrals of rational functions. The final answer is obtained by solving a large number of linear relations, which becomes challenging around 9 loops, basically because you get exponentially large number of terms. So people have distilled all the information that appears here in terms of polylogarithms in some symbolic language, in terms of a symbol. These L's that are called words are basically functions of the external momenta, Lorentz invariant combinations of the external momenta. You put them together in some particular way that reminds a word, because you put the letters together, you make a word, and you have to make a sentence, so you have to sum them with some coefficients that are integers. Okay? And if you know this symbol, then you can reconstruct the amplitude. Okay? But the number of elements in a symbol can be very large. For example, they look at a 3-gluon form factor, and it goes like 10 to the 12 at loop at 8 loops. But they can but in this language, you can formulate it. You can view it as a sentence, as a sequence to sequence task. Basically, it looks like language, so you can formulate it as a language task. And that's what they did. So in this paper, it involves Lance Dixon, involves people from Meta, etc. Notice in computer science, not in peptides. Okay? They use transformers with a few million of parameters to learn the sequences for a certain class of amplitudes in n equals 4 Sperry-Yang-Mills theory. And they made predictions of prediction of symbol coefficients where you train, on part of the L equals 4 data. Seems to be an easy task. So it reproduces all the rest with very high accuracy, like 99.9%. Then you can ask, does it learn all these linear relations, complicated linear relations? The answer is yes. They can see that it learns this as it trains. A more interesting thing, which again brings me back to what I wanted to achieve before, like generalize, go to where you cannot go, is whether there are any cross-loop relations. So for example, and the first baby step on that is basically if you train, suppose that you're interested in L equals 6 predictions, loop 6 predictions, but you also train it not only on L equals 6, you also give it the full L equals 5. Does it do better in L equals 6 tasks? And they see evidence that it does, okay? And their whole program, which is not finished yet, is basically to use this algorithm to make now predictions at higher loop levels, okay, where it's not possible to go with traditional techniques. So what's the summary? In part 1, we encountered examples of unsupervised learning. The algorithm generates its own data and trains to identify structures. Part 2, we encountered examples of supervised learning. Here we have to provide labeled data, and then it trains on those data. In the next and final part, in a few minutes, I will discuss another type of learning where one learns how to act. Okay? And I think that might be the bridge with the less traditional approach where the AI comes in as an equal partner and helps us in reasoning tasks. So, this is part 3, discovering new solution trust strategies, and this come under the name of reinforcement learning. So the idea here is basically it's the task that a robot has to do. So we're really discussing robots here, okay? So robots are inside some environment characterized by some states. They have to take some actions, okay? This is the action space. And then when they do something, they get a reward. Either their action is bad or good. And then they learn by doing, basically like humans learn, okay? By trial and error, okay? So, and this is a typical workflow of one of these algorithms that is called an actor-critic algorithm, where the agent takes an actions and takes feedback from the environment, that is the reward, gets some memory of its actions, then it updates its policy and retakes a step and so on and so forth. Where do neural networks come in here? Well, they come here as two types of neural networks. One basically calculates how good, what is the value of your state or your action, and the other one basically tells you with what probabilities you should take the next action. Okay, it's your policy. And this became quite popular when DeepMind basically was able to solve Go in this way. Okay, they were able to beat the world champion from South Korea in 5 games. There is a very nice 1.5-hour documentary of this. If you haven't seen it, it's really cool. Okay, and I will read it this one because it basically repeats what I said before. This is from the webpage of DeepMind. For the AlphaGo. We created AlphaGo, an AI system that combines deep neural networks with advanced search algorithms. One neural network, known as the policy network, selects the next move to play. The other neural network, the value network, predicts the winner of the game. Initially, we introduced AlphaGo to numerous amateur players of Go, so the system could learn how humans play the game. Then we instructed AlphaGo to play against different versions of itself, so it learns from itself. Okay? Each time learning from its mistakes, a method known as reinforcement learning. Over time, AlphaGo improved and became a better player. So in this documentary, you will see at some point when they play, I think, game 2, where the algorithm, the machine, makes a completely unexpected move that no human would ever do. That's move 37, okay? And then people just look at it and like, why did it make that move? And that move completely changes the game and gives the victory to the AI. Okay, and at that point they have this world champion saying, I thought AlphaGo was based on probability calculation and that it was merely a machine. But when I saw this move, I changed my mind. Surely AlphaGo is creative. Because people started studying now the way the algorithm was choosing strategies to learn how to play the game better. Okay, so that's really cool. So I have 2 examples here. I will go a little fast on them. One is from mathematics, work by Sergei Gugov and collaborators. One game that you can play in mathematics is you have nodes, you want to untangle them. Okay, so that's a nice game. It fits in this pattern. So nodes are circles embedded in R3. You project them on a plane, they look like this, and there are allowed moves that you can do to untangle them. Now, a knot may be an unknot. In other words, you can completely unknot it into a circle or not. Okay, so they wanted to used reinforcement learning to basically see if such an algorithm can play this game and unknot the knots. And this is an interesting game because it's also related to something known as the 4D Poincare conjecture in mathematics. So what is the state space? The space of braid words. They can parameterize it using numbers. It's discrete. Action space, all these allowed moves and the relations that these nodes obey. Reward, and the negative length of the braid word. So basically, it's a negative number. It tries to maximize it, make it large, and take it towards 0, make it small. Okay, make a smaller length. So RL significantly outperformed the random walker that selected right amongst all these moves from uniform distribution, and the rollouts identified sensible strategies. And in the later paper, they used this thing, used related techniques to rule out over 800 potential counterexamples to the smooth 4D Poincare conjecture. So mathematicians can use it. So we might be able to use it as well, okay, if the task is appropriate. Now, another example that we did with, again, with Kostis Papageorgakis at Queen Mary is we wanted to see if we can use similar strategies to apply them on the conformal bootstrap program to understand non-perturbatively conformal field theories, which describe the generic high energy and low energy behavior of quantum field theories. And the conformal bootstrap is, again, fits in this previous logic that I mentioned in the amplitude bootstrap. You do not try to solve traditionally. In the 6D 2,0 theory, there's no traditional method to follow. So trying to understand what are sensible and consistent answers is the way to go here. But you have to deal with an infinite number of algebraic conditions for an infinite set of CFT data. You see, again, dimensionality is the problem. Okay? So, and in a series of papers, we initiated the program aiming to solve these conditions with machine learning methods, and reinforcement learning was one of the methods that we used. We also used algorithms from people working in NASA for optimization. We used all sorts of different things, and we were able to get interesting results that were very competitive with the standard semi-definite programming methods that people are commonly using in the Bootstrap community. And this is a program that is still ongoing that goes towards an alternative to standard conformal bootstrap methods, applicable in more general situations where, for example, positivity is not possible. So this is my epilogue. In 2 minutes, I will be done. So let me circle back to the beginning of my talk. Okay. So the link is reinforcement learning. Okay, what this paper, the DeepSeek paper was mentioning is in abstract. What made it exceptional or very interesting was the fact that they were using reinforcement learning to induce reasoning. The large language model was not training by a lot of examples, which is the traditional method, which is called supervised fine-tuning. So you take a model, a foundational model, and the way you train it is you show it all of the internet. Okay. That allows you to build a base model, and then you want this model to have specific capabilities. Be good at reasoning, be a good physicist, be a good astrophysicist, or whatever, okay? Then you have to do further fine-tuning, and this is also costly. So this is the step that DeepSeek was able to bypass. How? By using reinforcement learning, by allowing the large language model to spend a lot of time thinking and developing its own reasoning capabilities. So both DeepSeek R1 and OpenAI SO1 models use reinforcement learning to increase their reasoning capabilities. Before answering a question, the LLM spends time to reflect on the answer, learning optimal reasoning strategies through trial and error. And they have this moment here in the DeepSeek paper, which they say that it's an aha moment for the model during training. It's also an aha moment for them. I mean, what it does here is not very important. The point is that when you give it a question, it doesn't go for the response immediately, but it has an intermediate stage where it's generating text and basically trying things on its own. So here what it did is it starts solving this equation, then it stops and says, wait. There's an aha moment that I can flag here, and then it goes back, basically the way we also think when we solve a problem. We say, oh, okay, maybe we should go back and rethink that step. So the crucial, what they are flagging here is the fact that it went back to rethink the problem.
So that's
okay?
different with ChatGPT.
ChatGPT is also doing that, but it's not open, so you don't know how they do it.
I've never noticed without giving a command that it goes back on its own.
No, this is happening, for example, this is happening internally. You won't see that. Okay. That's interesting. Okay, so the point here is that you're not hard coding everything, right? You're not hard coding, like all of these are features that are sort of emerging. Okay, this is really cool. So this is the last slide. So to summarize, recent developments in computer science are having a profound impact on scientific research. This is obvious. Okay, definitely in other fields. Theoretical physics is a latecomer to this game. More and more people are starting to think about this, and more papers come out in the archive. There are more and more groups that are basically trying to think about such problems. But I would hope, or I would like to argue, that it could be that theoretical physics, although it's a latecomer to this game, it might be an interesting playground for AI. Like, for example, Demis Hassabis, who is the co-founder of DeepMind, in this video in the beginning says, I think he comes from basically building games. And he says games are a very interesting context where AI can be developed. I think theoretical physics is also a very interesting context where potentially AI could develop. For theoretical physicists like us, it could be an opportunity to think about traditionally hard problems in a novel, out-of-the-way box. Because you see, in all these cases I mentioned, it wasn't really the AI that was really solving the hard part of the problem. It was us bringing the problem in a stage where it could admit a particular approach. And that, I think, could be a lot of fun. Okay, so thank you.
Questions, remarks from the audience?
I have a question about the false results that you said improve.
Could you speak a little bit louder?
So when you fed it false non-unitary cases,
Yeah.
was it completely a random one?
Yeah, completely random then. Completely.
Do you think it would be beneficial if they're close to being correct but they're still wrong and you put that in?
Top of my head, I would say no, but you can try. Because again, I don't have really an understanding of, how it would work. So usually, you have this idea, you just test it and see if it does better. So clearly, the thing that we did was like step one. Usually, I'm surprised that this thing is not something that people typically do. Like in this other paper, they have a similar problem with a symbol and the scattering amplitude bootstrap, but they don't do this step. They just train on true examples only. And I think it's something that could potentially benefit the whole process.
So in this like supervised learning that you said, like for this quantum mechanical problem,
yeah.
So when you specify this function that tells it whether it's correct or not,
yes.
So you use the equation that the exact equation that we know, right?
No. The only thing is there. I'm only working with finite partial wave functions, okay? And then all I do is basically, I think what we did was take two sets of random phase shifts. And then from these two completely random, so we generate two B phis, okay? And then we take B from one and phi from the other. So they're completely unrelated, okay? That's what we did. So, and then we tell it that's a wrong example. But we're not using the equation anywhere.
Yeah, but I mean, to specify whether the solution is correct or not.
We just use the fact that if we have a random generation, one random B and one random phi, the chances are that they're not going to be the B and a phi that corresponds to a single delta. In fact, we generate them with different deltas. So,
right, but then for the correct ones, I mean, you know.
For the correct ones, we just give the randomly chosen set of deltas, and then from the finite partial wave expansion, we read B and phi. We read the whole F. But we're not using the integral equation. Okay, that's the point. There is no integral equation anywhere.
Maybe I can ask something in the same spirit, Robert. Do you know an example you can illustrate the powerfulness of these methods where you know the solution, it's a single point in some huge parametric space, and you are able to corner it more and more, and at the end converge really to the known answer?
Well, I think some examples recently worked out by Sobkov in integrability had the spirit where they're looking for something which I think is an integer or something, and then they can corner with these methods the result, but they know it's an integer, so they can get the exact result in this way. So there are some cases where you can get exact results from these methods. Now, convergence is a more tricky business, and sometimes, for example, in the conformal bootstrap case, we have to make all sorts of approximations. So this also introduces systematic error, so it's more dirty.
given that we didn't care much about these things 2-3 years ago, do you think that the pace will be as fast in the next 5-10 years?
For our field?
Yeah.
For our field, I cannot predict, but there are more and more papers coming out, and I know more and more people that work on this stuff. Or I also hear from other people that Romuald was telling me that he has also been working on this. I know people, think about these things, although they may have not published something, they think about these things. So it's hard to tell. I think what's missing is there are all sorts of little applications in different domains. Perhaps some killer application where, it's something that we couldn't do and this thing really solves would be nice. Like for example, these people in DeepMind, they are precisely looking at these kinds of problems with this biology problem that gave them the Nobel Prize, or with AlphaGo. They are really selecting problems of very high visibility. When they are solved, they get the Nobel Prize. So if there's a killer application of this method, something that we really want to know and has high visibility, and someone uses one of these methods to solve it, I think it will go a long way. But again, yeah.
Okay. Thank you very much.
Thank you.